Hello there, and welcome to Just About Earth, where curiosity slows down, science takes its time, and the distant past becomes a quiet place to wander through before sleep. Tonight we're going to travel much farther back than most maps of Earth usually go, beyond the age of dinosaurs, beyond the age of forests and animals, even beyond the time when the continents we recognise today began to take shape. We are going to a world that existed so long ago that almost no landscape from it survives in a form we could recognise, a world called Colombia, sometimes known as Nuna, a supercontinent that came and went long before the more familiar Pangea ever formed. It is a strange thing to think about, really. When most of us picture ancient Earth, we imagine one vast landmass surrounded by a global ocean, perhaps dotted with volcanoes and shallow seas, with unfamiliar creatures wandering along the shorelines. But Colombia belonged to a much deeper past, a time when life was still microscopic, when the air itself was different, and when the rhythm of the planet followed rules that would feel quietly unfamiliar to us today. Before we drift too far into that ancient landscape, let me gently ask you something. Where are you listening from right now, and what time is it in your corner of the world? Perhaps it is late evening, the house settling into silence. Perhaps it is early morning and the sky outside is just beginning to brighten. Wherever you are and whenever you are, it is a pleasant thought that while we sit here in the present, we can let our minds wander billions of years into the past, to a planet that was both the same Earth we stand on and yet almost unrecognisable. If you find these quiet explorations soothing, or if you simply enjoy taking slow journeys through science and history, I would be very grateful if you gave the video a like and maybe subscribed. It helps this calm little space reach others who might also enjoy ending their day with a gentle walk through deep time. Now, let's begin to ease into the story. Picture the Earth, not as a blue and green globe with familiar continents, but as a young and restless world, still shaped by forces that were far more intense than what we experience today. The continents, if we can even call them that yet, were not arranged in the patterns we know. Instead, the surface of the planet was gradually assembling into something larger, piece by piece, over immense stretches of time. Colombia was one of the earliest supercontinents that scientists believe formed on Earth. It existed roughly between 1.8 and 1.5 billion years ago, a span of time so vast that it is difficult to grasp. If the entire history of Earth were compressed into a single year, Colombia would appear sometime in early autumn, long before the familiar events that fill most textbooks. And yet, despite being so ancient, Colombia was not a chaotic or alien place in every sense. It still had oceans, it still had weather. Rivers still flowed, though not across grassy plains or through forests of trees, but over bare rock and microbial mats, landscapes quiet and almost empty to our eyes. To understand this world, it helps to take a step back even further. Earth itself formed about 4.5 billion years ago, coalescing from dust and rock orbiting the young sun. At first it was a molten sphere, its surface glowing with heat, its atmosphere thick with volcanic gases. Over time the planet cooled, the crust solidified, and water began to accumulate, first as steam in the atmosphere, then as rain that fell for ages, filling the first oceans. Those early oceans were not peaceful places. They were warm, mineral-rich, and often stirred by volcanic activity beneath the surface. But within them, something remarkable happened. Life began, simple at first, single-celled organisms that fed on chemical energy or sunlight. These tiny living things would over hundreds of millions of years begin to change the entire planet. By the time Colombia formed, life had already been present for a very long time, yet it was still entirely microscopic. There were no plants, no animals, no fish or insects or birds. If you had stood on a shoreline during that era, the sea might have looked calm and empty, but just beneath the surface, trillions upon trillions of microorganisms were quietly shaping the chemistry of the oceans and the air. The continents themselves were also very different from those of today. Modern continents are built around ancient cores called cratons, fragments of crust that have survived for billions of years. Many of these cratons were already in existence during the time of Colombia, slowly colliding and merging under the slow but relentless motion of tectonic plates. Tectonic plates move at roughly the speed your fingernails grow, a pace so slow it seems almost motionless. But over millions of years, even that gentle movement can rearrange the entire surface of a planet. Imagine enormous slabs of rock, hundreds or even thousands of kilometers across, drifting across the mantle, colliding, folding, and rising into mountain ranges. Over time, these collisions stitch together the fragments of crust into a single immense landmass. That landmass, assembled piece by piece, was Colombia. Reconstructing the shape of Colombia is a bit like trying to solve a puzzle where most of the pieces have been worn down, broken, or buried. Scientists rely on clues preserved in ancient rocks, magnetic signatures locked into minerals, and the alignment of geological formations across continents that are now separated by vast oceans. For example, certain mountain belts in North America match in age and structure with formations in parts of Europe and Asia. These similarities suggest that those regions were once joined, part of a larger whole that existed long before the Atlantic Ocean ever formed. It is a quiet kind of detective work, piecing together fragments of evidence scattered across the globe, reconstructing a world that no human eyes ever saw. And what a world it was! The atmosphere during Columbia's time contained far less oxygen than today, though it was slowly increasing due to the activity of photosynthetic microorganisms. These tiny organisms released oxygen as a byproduct of their metabolism, gradually transforming the atmosphere in what scientists call the Great Oxidation Event, which had begun several 100 million years earlier and continued to shape the planet's chemistry. Breathing that air would not have been possible for us. Oxygen levels were too low and other gases were more abundant. But for the life forms of that era, it was simply the normal state of the world. The sky itself might have looked somewhat different as well. The sun, slightly dimmer than today, cast a softer light. Yet the Earth remained warm enough to maintain liquid oceans, a puzzle that scientists sometimes refer to as the faint young sun paradox. Somehow, greenhouse gases in the atmosphere help trap enough heat to keep the planet from freezing over completely. Days were shorter then too. The Earth rotated faster, meaning a full day may have lasted only around 18 or 19 hours. Imagine waking, working, and sleeping in a rhythm that repeated more quickly, sunrise and sunset arriving sooner than you might expect. The moon, meanwhile, was closer to Earth than it is now. Tidal forces were stronger, and the oceans would have risen and fallen with a slightly greater pull. Shorelines, where they existed, may have experienced more dramatic tidal changes, though without complex coastal ecosystems, the scene would have been stark and quiet. If you were somehow able to stand on the surface of Colombia, this silence might be the first thing you noticed. No wind rustling through leaves, no insects buzzing, no birds calling overhead. Only the sound of wind over rock, the distant crash of waves, and perhaps the rumble of volcanic activity far away. It is easy to think of such a world as empty, but that would not quite be true. Life was there, abundant in the oceans and in microbial communities that formed layered structures called stromatolites, some of which still exist today in a few places on Earth. These structures, built slowly by colonies of microorganisms, are among the oldest visible records of life on our planet. They grew in shallow waters, forming low, rounded mounds that rose centimetre by centimetre over centuries. Quiet, patient builders, shaping stone through biology. Time itself feels different when you think on these scales. Not years or centuries, but millions of years passing while continents drift, mountains rise and erode, and oceans open and close. Colombia itself did not appear overnight. Its assembly took hundreds of millions of years as smaller landmasses collided and fused. And once formed, it did not remain unchanged. The The forces that built it continued to reshape it, slowly preparing the stage for its eventual breakup. That is one of the great cycles of Earth's history, the supercontinent cycle. Continents gather together, forming a single vast landmass, and then, over immense spans of time, they fragment and drift apart, only to gather again in a new configuration. Pangea is only the most recent example. Before it came Rodinia. Before Rodinia came Colombia. And before Colombia there may have been even earlier supercontinents, though their traces are faint and difficult to interpret. Each cycle reshapes the climate, the oceans, and the evolution of life. Each cycle leaves behind clues in the rocks, waiting for someone to notice them hundreds of millions of years later. And so, as we settle into this story, we find ourselves standing at the beginning of Colombia's long existence, a world of ancient seas, quiet skies, and continents newly joined. In the distance, volcanoes release slow plumes into the air. Rivers carry minerals to the sea. Microbial life continues its patient work, molecule by molecule, gradually altering the atmosphere and preparing the planet for forms of life that will not appear for hundreds of millions of years yet. It is a reminder that the Earth we know today is only one version of a planet that has worn many faces. If we continue easing backward in time from the world of Colombia, the story becomes quieter, darker, and in some ways even more unfamiliar. The continents we have been picturing, those broad ancient cratons slowly merging into a single landmass, did not always exist in such recognizable forms. There was a time when Earth's surface looked far more fragmented, when the crust was thinner, the heat from the planet's interior stronger, and the entire system of tectonic plates behaved in ways that may have been faster, more restless, and less stable than today. To understand Colombia properly, it helps to imagine the long ages that prepared the planet for it, because a supercontinent does not appear suddenly. It is the result of processes unfolding over hundreds of millions of years, like a puzzle assembling itself piece by piece, long before anyone could have named the finished picture. Let's picture the Earth roughly 2.5 billion years ago. The sun hung in the sky, somewhat dimmer than today, though still bright enough to illuminate oceans that covered most of the planet. The air was different, containing far less oxygen and far more gases like methane and carbon dioxide. If you had stood there, the sky might not have looked quite the shade of blue we know now. The exact colour is still debated, but many scientists suspect it may have appeared hazier, perhaps with a faintly different tint due to the chemistry of the atmosphere. The land itself was sparse compared to modern Earth. Instead of vast continents, there were scattered pieces of crust, islands and proto-continents drifting across the surface of the mantle. Some were no larger than modern Greenland. Others were broader, but still far smaller than the continents we recognise today. These early fragments of crust were born in fire. Deep beneath the oceans, magma rose from the mantle, cooled, and hardened into basalt, the dark volcanic rock that still forms much of the ocean floor today. Over time, some of this crust thickened, melted again, and reformed into lighter rocks rich in silica, the kind that eventually builds continents. These lighter rocks floated slightly higher on the mantle, resisting subduction, surviving while denser crust was recycled back into the planet's interior. That is one of the quiet but important reasons continents exist at all. They are, in a sense, the survivors, the pieces of crust that managed to endure while others disappeared beneath the surface. During these distant ages, tectonic plates were already in motion, though possibly moving faster due to the greater internal heat of the young Earth. Collisions between fragments of crust built mountain ranges, while rifting events tore land apart again. It was a world in constant rearrangement, continents forming, breaking and reforming, in cycles far older than the one that eventually produced Colombia. And yet, despite the violence of volcanoes and the slow grinding of tectonic plates, the surface of the planet would not necessarily have felt chaotic all the time. Much of the activity unfolded over timescales so vast that a human observer, if one could have existed, might have experienced long periods of stillness, mountains eroding grain by grain, shorelines shifting so slowly that a lifetime would not reveal the change. The oceans of that era were different as well. Rich in dissolved iron, they sometimes carried a greenish tint, and in places, chemical reactions between oxygen produced by microorganisms and iron in the water created layers of rust-coloured minerals that settled on the seafloor. Over millions of years, these layers hardened into banded iron formations, rocks that today provide some of the clearest records of the early Earth's chemistry. It is a quiet image to hold in the mind, vast seas slowly depositing thin layers of minerals, year after year, century after century, until entire mountain ranges of iron-rich rock were laid down, all without a single fish or shell or coral reef to disturb the stillness. Life, however, was already there, and it was busy in its own microscopic way. Cyanobacteria, tiny organisms capable of photosynthesis, were spreading through the oceans, capturing sunlight and releasing oxygen as a waste product. At first, that oxygen did not accumulate in the atmosphere. It reacted with iron and other elements, becoming locked into minerals. Only after countless generations of these microorganisms had lived and died did oxygen begin to build up in the air. This gradual change transformed the planet in ways that would shape everything that followed. Oxygen is a reactive gas. It alters minerals, affects climate, and eventually enables more complex forms of life. But at the time, the process was slow, almost unimaginably slow, unfolding over hundreds of millions of years. While all this was happening, the fragments of continental crust continued drifting, colliding and welding together. Scientists believe that before Colombia, there may have been earlier supercontinents, sometimes given names like Kenorland, or even older proposed land masses whose existence is still debated. The evidence is fragmentary, preserved in rocks that have been buried, metamorphosed, and altered many times since. Trying to reconstruct those worlds is like trying to reconstruct a book after most of its pages have been burned and the remaining ones scattered across different continents. Yet careful study of mineral grains, isotopic signatures, and magnetic orientations in rocks allows geologists to piece together a surprisingly detailed picture. One of the clues comes from paleomagnetism, the record of Earth's magnetic field preserved in certain minerals as they cool from molten rock. These minerals align themselves with the planet's magnetic field, freezing in a tiny compass needle pointing toward what was then the magnetic pole. By studying the orientation of these minerals in rocks of different ages, scientists can estimate where those rocks formed relative to the poles, and by extension, where the continents themselves were located. It is delicate work, requiring careful measurements and an understanding that the magnetic field itself has reversed many times over Earth's history. Yet piece by piece, these measurements reveal patterns of movement, showing continents drifting, colliding and assembling into large configurations. Long before Colombia reached its full size, the groundwork was already being laid by these collisions. Mountain belts formed where land masses met, rising slowly over millions of years. Rain and wind began the patient work of erosion, wearing those mountains down and carrying sediments into the sea, where they hardened into new layers of rock. The cycle repeated again and again: uplift, erosion, deposition, burial, and uplift once more. It is one of the great rhythms of geology, a process so steady that it often goes unnoticed, yet so powerful that it can reshape entire continents. The climate of this earlier Earth also deserves a moment of quiet attention. Without large land plants to draw carbon dioxide from the air, greenhouse gases may have been more abundant, helping keep the planet warm despite the fainter sun. At times, however, Earth experienced dramatic glaciations, periods when ice spread across large portions of the surface. Some scientists believe that even before Colombia fully assembled, the planet may have undergone episodes of extensive glaciation, perhaps not as extreme as the later snowball Earth events, but still significant enough to leave traces in ancient rocks. Imagine glaciers moving slowly across bare rock landscapes, grinding stone into fine sediment, carving shallow valleys, and leaving behind deposits that would one day harden into rock, preserving the memory of ice long vanished. Meanwhile, beneath the surface, the mantle continued its slow convective motion, currents of hot rock rising and cooler rock sinking, driving the movement of tectonic plates above. This deep engine of the planet has been running for billions of years, shaping the surface in ways both subtle and dramatic. It is humbling to realise that the continents we live on today are only temporary arrangements, snapshots in a much longer story. Before Colombia, the land was scattered. After Colombia, it would scatter again, and in the far future, new supercontinents will form, reshaping the geography of the planet once more. Returning to the time just before Colombia began to assemble, the continents were like travellers gradually converging, drawn together by the slow choreography of plate tectonics. Each collision added new material, thickening the crust, stabilising regions that would become the ancient cores of continents. These stable cores, the cratons, are among the oldest surviving parts of Earth's surface. Some contain rocks more than 3 billion years old. They have endured collisions, rifting, burial and uplift, yet they remain silent witnesses to almost the entire history of the planet. If you were to stand on one of those cratons during that distant era, you might have seen a landscape of low hills, rocky plains and shallow seas. There would be no grass, no trees, no animals moving across the land. Only microbial mats clinging to damp surfaces, forming thin, textured layers that trapped sediment and slowly built up structures that could survive in the fossil record. The air would carry the scent of minerals and salt, perhaps a faint sharpness from volcanic gases. The wind would move across open terrain, unbroken by forests, unsoftened by leaves, and above the sky would stretch wide and empty, the stars brilliant at night in the absence of atmospheric pollutants, the Milky Way a bright river of light across the darkness. It is a peaceful image in some ways, though also stark, a reminder that life's complexity came much later. For most of Earth's history, the planet was inhabited only by microorganisms, and yet those tiny organisms transformed the world more profoundly than any forest or reef ever could. They changed the chemistry of the oceans, altered the atmosphere, and laid the groundwork for everything that followed. As the fragments of crust continued drifting closer together, the stage was being set for one of the largest continental assemblies the planet had yet seen. The collisions would intensify, mountain ranges would rise, and the scattered land masses would gradually merge into a single enormous continent. But that transformation did not happen overnight. It unfolded slowly, almost imperceptibly, as continents inched toward one another over tens of millions of years. And so, the Earth before the famous supercontinents was not a single unified world, but a patchwork, a mosaic of drifting lands and shallow seas, a planet in transition, quietly preparing for the moment when those pieces would finally come together to form Colombia, a world that, even in its own time, was only one phase in a story that continues to unfold beneath our feet even now. So what exactly was Colombia, sometimes called Nuna, and how can we possibly know anything about a world that disappeared more than 1 billion years ago? It is a reasonable question, because unlike Pangea, whose outlines can almost be guessed by looking at a modern globe, Colombia left behind no obvious map. The oceans that once surrounded it have opened and closed many times since. Mountain ranges that rose during its assembly have been worn down, buried, or reshaped. Even the rocks themselves have often been heated, compressed, and transformed so deeply that their original forms are difficult to recognise. And yet, despite all of this, scientists are surprisingly confident that Colombia existed, not because of a single piece of evidence, but because of many different clues that, when placed together, tell a consistent story. One of the first hints came from the ages of rocks. Across different parts of the world, geologists began to notice something curious. Large regions of continental crust in North America, Northern Europe, Siberia, India, and parts of China contained rocks that formed at roughly the same time, between about 2.0 and 1.8 billion years ago. These rocks were not isolated or random. Many showed signs of having been created during massive continental collisions, events powerful enough to produce vast mountain belts. Mountain building on that scale does not happen in small scattered fragments. It usually requires large land masses colliding, welding together, and forming something bigger. When geologists compared these belts across continents, they began to suspect that many of them were once part of a single connected system. Imagine finding pieces of a broken ceramic plate scattered across a room. Each piece by itself might not tell you much, but if the edges match, the patterns line up, and the material is the same, you begin to realize that they once belonged together. That is essentially what geologists were seeing in the rocks of different continents. Structures that looked like fragments of the same ancient collisions, now separated by oceans thousands of kilometers wide. Another important clue came from paleomagnetism, which we touched on earlier. When molten rock cools, tiny magnetic minerals inside it align with Earth's magnetic field, locking in a record of the latitude at which the rock formed. By studying these magnetic signatures, scientists can estimate where pieces of crust were located at different times in the past. When researchers compared paleomagnetic data from ancient rocks of similar age across several continents, they found patterns suggesting that those landmasses had once been positioned close together. Not perfectly overlapping, because uncertainties always remain, but close enough to support the idea of a large unified continent. Of course, reconstructing a vanished world is never straightforward. The farther back in time you go, the fewer intact rocks remain. Plate tectonics constantly recycles the surface, pushing oceanic crust back into the mantle and reshaping continental edges. It is as if the Earth is continually rewriting its own surface, leaving only fragments of earlier drafts behind. This means that any reconstruction of Colombia is, in some sense, a best approximation, a careful model built from incomplete information. Scientists debate the exact arrangement of its pieces, and different reconstructions place certain regions in slightly different positions. But the overall picture, a vast supercontinent assembled between about 1.9 and 1.8 billion years ago, is widely accepted. What might that continent have looked like? Instead of imagining a single smooth landmass like a modern political map, it is better to picture a broad, irregular shape made up of ancient cratons joined by belts of younger rock. Some regions were probably mountainous, where collisions had recently occurred. Others were lower, worn down by erosion into plains and shallow basins. Rivers would have flowed across these landscapes, carrying sediments toward the sea. Without land plants to hold soil in place, erosion may have been intense in some areas, with sediments washing quickly into shallow coastal waters. These sediments, layer upon layer, would later harden into sandstones and shales, preserving subtle records of ancient environments. The coastlines themselves may have been long and complex, with shallow seas extending far inland in some regions. These shallow waters were important habitats for microbial life, which thrived in sunlit environments where photosynthesis was possible. It is interesting to consider that while Colombia was enormous by human standards, it did not necessarily cover all land on Earth at every moment of its existence. Some smaller fragments of crust may have remained separate, island-like, drifting nearby before eventually joining or moving away again. Supercontinents are not always perfectly unified in the way we sometimes imagine. They are dynamic systems, continually adjusting, with edges that shift, rift, and sometimes break apart even as other regions remain firmly joined. The name Colombia itself was proposed by geologists in the late 20th century, though the alternative name Nuna is also widely used, particularly in European and Asian research. Both names refer to the same general idea, an early Proterozoic supercontinent assembled long before Rodinia and Pangea. The choice of names reflects the collaborative nature of geology. Scientists from different countries and traditions contribute pieces of evidence, and over time, a shared picture emerges, even if different terms are sometimes preferred. Reconstructing Colombia is not only about rocks and magnetism, it also involves studying the chemistry of minerals, the ages of zircons, and the isotopic signatures locked inside crystals that formed billions of years ago. Zircon crystals, in particular, are extraordinary timekeepers. They can survive processes that destroy most other minerals, and they often contain tiny amounts of uranium that decay into lead at a known rate. By measuring the ratio of uranium to lead, scientists can determine the age of a zircon crystal with remarkable precision, sometimes within a few million years, even for rocks billions of years old. These crystals are like tiny clocks, ticking silently through deep time, preserving records of volcanic eruptions, mountain building and continental collisions. When zircons of similar ages and compositions are found in rocks now separated by oceans, they provide another clue that those regions were once connected or shared a common geological history. But reconstructing a vanished world is not only a matter of assembling data, it also requires imagination, a careful, disciplined imagination grounded in evidence, but willing to picture landscapes that no one has ever seen. What would it have felt like to stand on Colombia? The land might have stretched for thousands of kilometers without encountering an ocean, depending on where you stood. The air would have been thinner in oxygen, the sky perhaps slightly different in tone, the sun a little dimmer. Storms would still have formed, rain would still have fallen, rivers would still have carved valleys, but the absence of plants and animals would have made the land feel stark and open. The ground underfoot would have been bare rock, gravel or microbial mats, with no grass to soften the landscape. In coastal regions, tides would have risen and fallen, perhaps leaving behind broad flats where thin films of microorganisms coated the sediment, forming slippery layered surfaces. At night, the stars would have been brilliant, the Milky Way clearly visible in the dark sky, uninterrupted by artificial light or atmospheric haze from modern industry. There is something quietly peaceful in imagining such a world, a planet still in the long middle of its story, shaped by forces that move slowly but with immense power. Another aspect of Colombia that scientists study is its internal structure. Not just its surface geography, but the way its pieces were assembled. When continents collide, they form what geologists call orogenic belts, zones of intense deformation where rocks are folded, faulted and metamorphosed under high pressure and temperature. These belts often remain visible in the geological record long after the mountains themselves have eroded away. By mapping these belts across different continents and matching their ages and characteristics, scientists can trace the lines along which ancient landmasses were joined. It is a bit like tracing the seams of a garment to understand how it was stitched together. In the case of Colombia, several major orogenic belts around the world appear to be roughly the same age and to share similar histories. This suggests that they formed during the same broad period of continental assembly, reinforcing the idea that a large supercontinent existed at that time. The ocean surrounding Colombia also played an important role in shaping its history. Oceanic crust forms at mid-ocean ridges and is eventually subducted back into the mantle at trenches. This continuous recycling means that almost no oceanic crust older than about 200 million years survives today. As a result, the oceans that surrounded Colombia have completely vanished, leaving only indirect evidence of their existence. That evidence comes from sediments deposited along ancient continental margins, as well as from fragments of oceanic crust that were scraped off and preserved during subduction. These fragments, called ophiolites, sometimes provide rare glimpses of ancient ocean floors. From such clues, scientists infer that Colombia was surrounded by vast oceans, perhaps larger than any we know today, and that the circulation of those oceans influenced climate, chemistry, and the distribution of life. Another interesting question concerns how long Colombia existed as a coherent supercontinent. Evidence suggests that it remained largely assembled for several 100 million years, a remarkably long time by geological standards. During this period, tectonic activity continued, but the major continental blocks remained joined, forming a stable configuration. Eventually, however, the same forces that brought the continents together began to pull them apart. Heat building beneath the crust, changes in mantle convection, and the gradual accumulation of stress along rifts led to the fragmentation of Colombia, setting the stage for the next chapter in Earth's supercontinent cycle. But that story belongs a little farther ahead in our journey. For now, it is enough to picture Colombia as a vast and ancient landmass, assembled from pieces of crust that had travelled long distances to meet, shaped by collisions that raised mountains and carved basins, surrounded by oceans rich in microscopic life, and illuminated by a sun slightly dimmer than the one shining today. It was a world that existed for hundreds of millions of years, yet left behind only fragments of itself, scattered across the continents we know now. And perhaps that is part of what makes it so fascinating. Colombia reminds us that the Earth we see today is only one arrangement among many, a temporary configuration in a long and ever-changing story. Continents move, oceans open and close, climates shift, and life evolves, all on timescales so vast that even entire mountain ranges come and go like passing weather. Long before anyone used the name Colombia or Nuna, the idea that such a continent might have existed was not obvious at all. For much of scientific history, people assumed that the continents had always looked more or less the way they do now, perhaps shifting a little here and there, but not assembling into enormous land masses and then breaking apart again. The realization that Earth's surface moves, and has always moved, took time to emerge, and the discovery of ancient supercontinents came only after several different lines of evidence slowly began to converge. The story really begins with something quite simple: maps. In the early 20th century, a German meteorologist named Alfred Wegener noticed that the coastlines of South America and Africa seemed to fit together rather neatly, like two pieces of a puzzle. At first glance it might have seemed like a coincidence, but Wegener looked deeper. He compared fossils, rock formations, and geological structures on both sides of the Atlantic and found striking similarities. It appeared that these continents had once been joined. Wegener proposed the idea of continental drift, suggesting that the continents had once formed a single land mass and later separated. At the time, many scientists were skeptical. The idea was bold, but Wegener could not explain exactly how continents moved. Without a convincing mechanism, the theory remained controversial for decades. Then, in the mid-20th century, evidence from the ocean floor began to change everything. Researchers mapping the seabed discovered mid-ocean ridges, long underwater mountain chains where new crust was forming. They also found symmetrical patterns of magnetic stripes on either side of these ridges, recording reversals in Earth's magnetic field as molten rock cooled and hardened. These discoveries revealed the process of seafloor spreading. New crust forms at ridges, moves outward, and is eventually recycled into the mantle at subduction zones. The continents, resting on tectonic plates, are carried along by this slow motion. With plate tectonics established, Wegener's idea of drifting continents was finally understood as part of a larger system. Scientists began reconstructing past positions of continents, first for relatively recent times, then for deeper and deeper periods in Earth's history. Pangea, which existed about 300 million years ago, became the first widely accepted supercontinent reconstruction. Its outlines were relatively clear because the continents had separated only recently in geological terms, and many matching features remained visible. But once scientists realized that continents could assemble into supercontinents and then break apart, a natural question followed. Had this happened before Pangea? Answering that question required looking much farther back in time, into rocks that were older, more altered, and often harder to interpret. It meant learning to read clues that were subtle and sometimes incomplete. One of the most important tools in this work turned out to be paleomagnetism, a method that sounds technical but rests on a simple principle. When certain minerals form, especially in molten rock that cools and solidifies, they align themselves with Earth's magnetic field, like tiny compass needles frozen in place. Because the magnetic field has a known relationship to latitude, these minerals preserve a record of where on the globe the rock formed. By studying many rocks of different ages, scientists can trace how continents moved over time. The work requires patience. Samples must be collected carefully, often from remote regions. They're cut into small specimens, measured in laboratories, and analysed to determine the direction of magnetization. Then the data must be corrected for later tilting or deformation of the rocks, a process that demands careful reasoning and cross-checking. When researchers began applying these methods to very old rocks, patterns started to appear. Rocks of similar age from different continents sometimes showed paleomagnetic signatures suggesting that those continents had once been located close together. At the same time, geologists studying mountain belts noticed similarities in age and structure across widely separated regions. Mountain belts form when continents collide, and they leave behind distinctive patterns of folded and metamorphosed rocks. If two continents share mountain belts of the same age and composition, it is often a sign that they were once joined. Over the years, more and more of these connections were identified. Ancient rocks in North America showed similarities to rocks in Greenland, Scandinavia, and parts of Russia. Regions in India, Australia, and Antarctica revealed matching geological histories in certain time periods. Individually, each piece of evidence was suggestive but not decisive. Together, they began to form a picture of a large landmass that must have existed between about 1.8 and 1.5 billion years ago. The process of reconstructing that landmass was slow and sometimes uncertain. Scientists proposed different arrangements, tested them against new data, revised their models, and tried again. It was not a single discovery, but a gradual realization, emerging from decades of work by many researchers around the world. One particularly important line of evidence came from the study of zircon crystals. These tiny minerals, often smaller than a grain of sand, can survive geological processes that destroy most other materials. They contain trace amounts of uranium, which decays into lead at a predictable rate, allowing scientists to determine the age of the crystal with great precision. Zircons also preserve information about the conditions under which they formed. By comparing zircons from different regions, researchers can identify episodes of continental growth, volcanic activity, and mountain building. When zircons of similar ages and characteristics appear across multiple continents, it often indicates that those regions shared a common geological history. In some cases, zircons eroded from ancient mountains were carried by rivers and deposited in sediments far away. These sediments later hardened into rock, preserving the zircons as tiny time capsules. By studying them, scientists can trace connections between distant areas, linking fragments of crust that were once neighbours. Another valuable source of information comes from isotopic analysis, the study of variations in the composition of elements such as neodymium and strontium in rocks. These isotopes act like chemical fingerprints, revealing the origins of the materials that form the rocks. Matching isotopic signatures across continents can provide further evidence that those regions were once part of the same system. Fieldwork also plays a crucial role. Geologists spend months or even years mapping rock formations, measuring structures, and collecting samples. They climb mountain ranges, traverse deserts, and work in polar regions, often in difficult conditions, all to gather the pieces of evidence needed to reconstruct ancient Earth. It is a kind of exploration that unfolds slowly, without the drama of rockets or submarines, but with its own quiet sense of discovery. Each outcrop, each thin section of rock examined under a microscope, adds another detail to the picture. Over time, as more data accumulated, the idea of Colombia became increasingly solid. The timing of continental collisions, the distribution of rock types, and the paleomagnetic data all pointed toward the existence of a supercontinent assembled roughly 1.8 billion years ago. Of course, there are still debates about the exact arrangement of its parts. Some researchers propose slightly different configurations, placing certain cratons in different positions relative to one another. These disagreements are part of the normal process of science, where models are refined as new evidence emerges. It is worth remembering that reconstructing a world this old is extraordinarily challenging. Most oceanic crust from that era has long since been recycled into the mantle. Many continental rocks have been metamorphosed, erasing or altering their original features. Entire mountain ranges have been worn down to plains. In a sense, scientists are trying to reconstruct a landscape after most of the evidence has been scattered, buried, or transformed. The fact that they can do it at all is a testament to the ingenuity of the methods they have developed. Technology has also played an increasing role. High-precision instruments can measure isotopic ratios to astonishing accuracy. Satellite data helps map geological structures in remote areas. Computer models simulate plate motions and test whether proposed reconstructions are physically plausible. Yet despite all these tools, the process still depends heavily on careful observation and reasoning. Rocks do not announce their histories clearly. They must be questioned, compared, and interpreted. There is also a certain humility in this work. Scientists know that their reconstructions are approximations, the best possible interpretations based on available evidence, but always open to revision. New discoveries can shift the picture, adding detail or sometimes changing assumptions. That willingness to revise ideas is one of the strengths of science. It allows understanding to grow steadily, becoming more accurate over time. Another fascinating aspect of discovering Colombia is that it required scientists to think on timescales far beyond ordinary experience. Human history spans thousands of years. Even the rise and fall of civilizations covers only a tiny fraction of geological time. Colombia existed more than 1 billion years ago, in an era so distant that even complex life had not yet appeared. To work on such timescales requires a different kind of imagination, one grounded in evidence but comfortable with vast stretches of time. It means thinking in millions of years as easily as we think in days or months. As the evidence accumulated, the picture of Colombia became clearer. It was not just a theoretical possibility, but a real stage in Earth's history. A supercontinent that formed, persisted for hundreds of millions of years, and eventually broke apart, setting the stage for later configurations like Rodinia and Pangea. And yet, despite all this knowledge, Colombia remains in some ways mysterious. We do not know exactly what its landscapes looked like in detail, or precisely how its coastlines were shaped. We cannot walk across its plains or watch its tides. We know it through traces, through fragments, through the language of rocks and minerals. Perhaps that is part of what makes the story so compelling. It reminds us that the Earth has a deep history, much of it hidden, waiting to be uncovered by patient observation and careful reasoning. If you could somehow step outside the present and look down at Earth during the time of Colombia, the first impression would be unfamiliarity. Not dramatic in the sense of chaos or violence, but unfamiliar in quieter ways, in the shapes of coastlines, in the colours of the land, in the absence of things we take for granted without noticing them. There would be no forests, no grasslands, no flowers, no insects drifting in warm air, no birds crossing the sky. The land would not be green. Instead, it would appear mostly in shades of brown, grey, black and reddish tones, where iron-rich rocks were exposed to the atmosphere. In some regions, the surface might even carry a faint purplish or dark film, where microbial communities covered damp ground near the edges of shallow water. From orbit, the planet would still be blue, because oceans dominated the surface then as they do now. but the patterns of blue and land would look unfamiliar. The great continents we know today would not exist in their present forms. Instead, a vast supercontinent stretched across part of the globe, its boundaries irregular, its interior dry in places, its margins broken by shallow seas. Cloud systems would drift across the oceans much as they do today, because the physics of air and water had not changed. Storms formed then just as storms form now. Winds carried moisture inland. Rain fell, gathered into streams, and rivers slowly carved channels across bare rock. Yet even something as simple as a river would have looked different. Without roots to hold soil in place, riverbanks were more unstable. Sediment washed more freely, and rivers may have shifted their courses more often, spreading wide fans of sand and mud across low plains. In flood seasons, the water would have turned thick with suspended particles, carrying minerals toward the sea. If you stood beside one of those rivers, the silence might strike you first. No insects humming, no frogs, no birds calling across the water. Only the sound of moving current, wind against stone, and perhaps the distant rumble of thunder. The air itself would feel different to breathe, though not necessarily unpleasant in every sense, if breathing were possible at all. Oxygen levels were lower than today. Not dangerously low for short exposure perhaps, but certainly not comfortable. The atmosphere contained higher amounts of carbon dioxide and other gases, influencing both climate and the colour of the sky. Scientists debate exactly how the sky would have appeared, but many believe it may have been slightly hazier, especially in coastal or volcanic regions. The sun, about 10% dimmer than it is now, would still have provided ample light, though sunsets might have taken on subtly different hues depending on the composition of the atmosphere. Day and night would also have followed a slightly faster rhythm. Earth rotated more quickly then, meaning shorter days, perhaps around 18 or 19 hours long. Morning would arrive sooner than expected. Night would fall earlier. Over the course of a year, there would be more sunrises and sunsets than we experience now, though the year itself, measured in the planet's orbit around the Sun, remained roughly the same length. The Moon would have been closer, appearing slightly larger in the sky. Tides would have been somewhat stronger, especially along broad, shallow coastlines. In places where the sea met gently sloping land, tidal flats may have stretched for great distances, exposed and flooded in steady cycles, leaving behind layers of sediment that hardened into rock over immense spans of time. These tidal flats were among the most active environments for life in that era, though the activity was microscopic. Thin layers of cyanobacteria and other microorganisms formed mats across wet surfaces, trapping grains of sand and building layered structures over time. These formations, called stromatolites, were common in shallow marine environments and still survive today in a few places, offering a small window into what those ancient shorelines may have looked like. Seen from a distance, a field of stromatolites might have resembled low, rounded mounds rising from shallow water, their surfaces slick and dark, their growth so slow that centuries passed before noticeable changes occurred. Beyond the coastlines, the interior of Colombia may have been dry in many regions, especially far from the influence of moist ocean air. Large continental interiors tend to experience more extreme climates, and without forests or grasslands to moderate temperature and moisture, the land could have been stark, with wide expanses of exposed rock and sediment. Dust storms may have been common in some areas, lifting fine particles into the air and carrying them across the landscape. Over time, these sediments settled in basins and shallow seas, forming layers that would eventually become sandstones and shales. Volcanoes also played a significant role in shaping the environment. The Earth's interior was still warmer than today, and tectonic activity was vigorous. In regions where plates were pulling apart or colliding, magma rose to the surface, forming volcanic chains and releasing gases into the atmosphere. Some eruptions would have been quiet, producing slow flows of lava that spread across the land. Others may have been explosive, sending ash high into the sky and covering nearby regions in fine volcanic dust. Over millions of years, repeated eruptions built up thick layers of igneous rock, contributing to the growth of continental crust. If you had travelled across Colombia over the course of thousands of kilometres, you would have seen landscapes shaped by these forces, mountain ranges rising where continents had collided, broad plains worn down by erosion, shallow inland seas reflecting a pale sky, and always the sense of vastness, of open space unbroken by forests or cities, of a planet still early in its long history of biological transformation. The oceans themselves were also different, though at first glance they might have looked familiar. Waves still rolled toward shore, storms still stirred the surface. But beneath the water, the chemistry was not the same as today. Oxygen levels in the deep ocean were lower, and in some regions the water may have been stratified, with layers differing in temperature and composition. Iron, dissolved in seawater, sometimes reacted with oxygen produced by microorganisms, forming particles that settled to the seafloor and contributed to the banded iron formations found in ancient rocks today. These layers, alternating between iron-rich minerals and silica, built up slowly, recording subtle changes in ocean chemistry over millions of years. Today they are mined in many parts of the world, providing iron used in buildings, machines and bridges, materials derived from processes that unfolded in silent seas more than 1 billion years ago. Marine life at that time was entirely microscopic, yet incredibly abundant. Bacteria, archaea, and simple algae filled the oceans, forming the base of ecosystems that were invisible to the naked eye, but immense in scale. They captured sunlight, processed nutrients and released oxygen, gradually transforming the atmosphere and oceans. Without larger organisms to graze on them, microbial communities could grow in thick layers, forming biofilms across rocks and sediments. In some environments, these communities influenced the formation of minerals, creating textures and structures that geologists can still recognize today. The absence of animals meant that many ecological processes we take for granted did not exist. There were no predators hunting prey, no burrowing creatures stirring sediment, no reefs built by corals or shellfish. The seafloor in many places was smooth and undisturbed, with fine layers of sediment settling gently year after year. Weather patterns, however, were already complex. The rotation of the planet, the distribution of land and sea, and the energy from the sun drove atmospheric circulation much as they do now. Winds carried moisture from oceans inland. Storm systems formed along temperature gradients. Rain fell, rivers flowed, and evaporation returned water to the sky. Climate during the time of Colombia appears to have been generally warm, though not uniformly so. There is evidence of glaciations in certain periods, indicating that the planet could still experience significant cooling. These glacial episodes left behind deposits of rock and sediment that show signs of having been carried and shaped by ice. Imagine glaciers moving slowly across bare terrain, grinding rock into fine powder, carving shallow grooves into the surface. Over thousands of years they would advance and retreat, leaving behind evidence of their passage in layers of till and striated stone. The causes of these glaciations are still studied. Changes in atmospheric composition, volcanic activity, and the arrangement of continents may all have played roles. The Earth's climate system has always been sensitive to subtle shifts, even long before humans began influencing it. Another difference in that ancient world was the brightness of the night sky. Without artificial lights, without aircraft crossing overhead, without satellites reflecting sunlight, the stars would have appeared extraordinarily vivid. The Milky Way would stretch across the sky as a luminous band, bright enough to cast faint shadows under dark conditions. The moon, slightly closer, would dominate the night, its phases marking the passage of time long before any living creature could observe them with understanding. It is a quiet thought that the rhythms of day and night, of tides and seasons, were already established, long before there were eyes to see or minds to measure them. Geologically, Colombia was not static. Even during the hundreds of millions of years when it existed as a supercontinent, the forces beneath the surface continued to reshape it. Heat accumulated beneath thick continental crust, sometimes causing rifting where the land began to pull apart. In other regions, smaller land masses collided with the edges of the continent, adding new material and altering coastlines. Mountain ranges rose and were worn down again, sediments filled basins, and the slow cycle of uplift and erosion continued without pause. If you could watch the continent over millions of years, you would see coastlines shifting, rivers changing course, volcanic islands appearing and disappearing. But on the timescale of a human lifetime, the land would appear almost motionless, its changes too slow to notice. There is something calming in that thought, the idea that beneath all the activity of our modern world, the deeper processes of the planet continue at their own steady pace, just as they did more than 1 billion years ago. The Earth during the time of Colombia was not a lifeless world, nor was it a world of dramatic, constant upheaval. It was a planet in balance, shaped by wind and water, by heat rising from the mantle, by microscopic life altering the chemistry of oceans and air. It was a world that looked completely different from our own, yet followed the same fundamental laws of physics, the same cycles of energy and matter that still govern the planet today. Looking more closely at the land itself during the time of Colombia, what stands out first is that the continents were not smooth, uniform surfaces. Just as today, the terrain was shaped by collisions, uplift, erosion, and the slow rearrangement of crust over immense spans of time. The difference was not in the existence of mountains or coastlines, but in their character and in the deep age of the foundations beneath them. At the heart of Colombia were cratons, the ancient cores of continents. These are some of the oldest surviving pieces of Earth's crust, regions that have remained stable for billions of years. Even today, large parts of North America, Africa, Australia and Eurasia sit atop cratons formed in the distant past, some older than 3 billion years. During the time of Colombia, many of these cratons were already ancient. Their rocks hardened, cooled and thickened through countless earlier episodes of volcanism and collision. Cratons are sometimes described as the anchors of continents. They are thick, buoyant, and resistant to being recycled back into the mantle. While oceanic crust is continually formed and destroyed, cratons endure, drifting slowly across the planet but rarely disappearing entirely. Colombia was, in many ways, a gathering of these ancient fragments, stitched together by mountain belts formed where they collided. Imagine vast regions of rocky terrain, low in relief in some areas, rising into rugged highlands in others. The oldest cratonic interiors may have been relatively flat, worn down by long ages of erosion, while younger belts at their edges were more rugged, shaped by recent tectonic activity. Mountains during this era could be immense, though they would not remain so forever. When continents collide, the crust crumples and thickens, pushing peaks upward. Over time, wind, rain and temperature changes begin to wear those peaks down, carrying sediments away grain by grain. The process is slow, but relentless. A mountain range that takes tens of millions of years to rise can be worn down over similar spans of time, leaving behind rolling hills or even flat plains, with only the roots of the mountains preserved deep in the crust. Some of the mountain belts formed during the assembly of Colombia were enormous by any standard, stretching thousands of kilometers. Today, geologists recognize their remnants in places where ancient rocks have been exposed again by erosion. These remnants, though often subdued compared to younger ranges like the Himalayas, tell stories of collisions that shaped the early continents. Between the cratons and mountain belts lay basins, low-lying regions where sediments accumulated. Rivers carried sand, silt and clay from the highlands into these basins, where the material settled in layers. Over time, pressure and chemical changes transformed these layers into sedimentary rock, preserving records of ancient environments. Without plants to stabilize the soil, Erosion may have been more intense than in many modern landscapes. Rainfall could wash loose material into rivers quickly, and seasonal floods may have spread sediments across broad plains. In some places, shallow lakes or inland seas may have formed, reflecting the sky and slowly filling with sediment over thousands of years. Coastlines during the time of Colombia were likely extensive and varied. Where the land met the sea, waves shaped rocky shores, while in other regions gentle slopes allowed the ocean to spread far inland, forming shallow continental shelves. These shallow waters were among the most active environments on the planet, not because of large organisms, but because of microbial life thriving in the sunlight. Stromatolites, those layered structures built by microorganisms, were common in such environments. They grew slowly, forming low domes and ridges in shallow water. Over time, entire fields of stromatolites could develop, creating textured landscapes just beneath the surface of the sea. Standing on one of those ancient shores, the scene would have been quiet and stark. The water might have been clear in some places, cloudy in others where sediment washed in from rivers. The tide would rise and fall, exposing flats of wet sand or mud, sometimes coated with thin films of microbial life. The absence of plants and animals would make the coastline feel almost empty to modern eyes, yet subtle signs of activity would be everywhere. Patterns in the sediment left by retreating water, layers forming in microbial mats, occasional ripples carved by currents. Farther inland, the land might rise gradually toward hills or mountains, their slopes bare except for scattered microbial colonies clinging to damp rock surfaces. Weathering would slowly break down exposed rock, creating soils that were thin and mineral-rich, but lacking the organic material that gives modern soil its dark colour and fertile structure. The colours of the landscape would likely be dominated by the natural hues of rock, reddish iron oxides, grey granites, darker volcanic basalts, and pale sandstones. In some regions, chemical weathering under different atmospheric conditions may have produced colours that would seem unusual to us. Subtle variations in tone reflecting the chemistry of air and water at the time. Volcanic regions added another dimension to the terrain. Lava flows spread across the surface, cooling into black or dark grey rock. Over time, these flows fractured and weathered, creating rough, uneven ground. Ash from eruptions settled in layers, sometimes carried far by the wind before falling back to the surface. These volcanic landscapes could remain active for long periods, with new eruptions reshaping the terrain again and again. Hot springs and hydrothermal vents may have dotted some regions, releasing mineral-rich water and supporting specialised microbial communities. Tectonic forces also created rift valleys in some areas, places where the crust was being pulled apart. These valleys could fill with water, forming long narrow lakes or shallow seas. Over time, continued rifting might eventually lead to the formation of new ocean basins, though such processes unfolded over millions of years. It is interesting to consider how different the concept of distance might have felt in such a world. Without forests or cities, without roads or cultivated land, the landscape would stretch unbroken for enormous distances. A mountain range on the horizon might lie hundreds of kilometres away, its outlines softened by haze. Travel across such terrain, if it had been possible, would have been slow and difficult, not because of vegetation or human structures, but because of the rawness of the land itself, the uneven ground, the lack of clear pathways, the constant exposure to wind and weather. Another feature of Colombia's land was the thickness of the continental crust itself. When continents collide, the crust can thicken to great depths, forming roots that extend far below the surface. These thickened regions are stable and resistant to deformation, helping preserve ancient rocks over billions of years. In some parts of Colombia, these thick crustal roots may have influenced the climate by affecting elevation and weather patterns. High plateaus can alter atmospheric circulation, creating rain shadows and influencing the distribution of moisture across the land. The interplay between geology and climate was already shaping the planet in subtle ways. Mountains influenced wind patterns, rivers carried nutrients to the sea, volcanic eruptions released gases that affected atmospheric composition. Even in the absence of complex life, the Earth was an interconnected system, with processes in one part of the planet influencing conditions elsewhere. Over long spans of time, erosion would gradually lower mountain ranges, filling basins with sediment and creating broad plains. New tectonic movements would raise other regions, continuing the cycle. The land was never static, though its changes were usually too slow to notice on human timescales. Looking at the ancient cratons that still exist today offers a glimpse into this distant world. In places like the Canadian Shield, parts of Australia, and regions of Africa, vast expanses of ancient rock are exposed at the surface. These landscapes, though altered by more recent processes, still preserve something of the character of very old continental interiors, rocky terrain, sparse soil, and a sense of deep time written in the stone. During the time of Colombia, such terrains would have been even more widespread, forming the stable cores around which younger rocks were added. The continent was a mosaic of old and new, ancient cratons joined by younger belts, shaped by collisions that left their marks in folded and metamorphosed rock. Coastlines shifted slowly as sea levels changed, influenced by tectonic movements and climatic variations. In some periods, shallow seas may have flooded large areas of the continent, depositing layers of limestone and other sediments. In other times, falling sea levels exposed broad stretches of land, allowing rivers to cut deeper valleys. The rhythm of transgression and regression, the advance and retreat of the sea, was already part of Earth's story, long before humans began measuring tides or charting shorelines. If you imagine standing on a high ridge overlooking the land of Colombia, the view would be vast and quiet. Hills and plains stretching to the horizon, a distant line of mountains fading into the haze, a river glinting in the sunlight as it wound its way toward a distant sea. No cities, no roads, no fields, only rock, water, wind, and sky. And yet, beneath that quiet surface, the forces shaping the planet were as active as ever. Plates moving, magma rising, mountains forming and wearing away. The shape of the land was always changing, even if the changes unfolded slowly, over spans of time that dwarf human history. Understanding the shape of Colombia's land is not only about imagining its mountains and shores, it is also about recognizing that these ancient features laid the groundwork for what would come later. The stability of cratons, the patterns of mountain building, the distribution of sediments, all of these influenced the next stages of Earth's history, guiding the formation of later supercontinents and shaping the environments in which life would continue to evolve. Beyond the rocky coasts and wide continental interiors of Colombia stretched oceans that would have seemed at once familiar and profoundly different. Water still covered most of the planet, waves still rose and fell under the pull of wind and gravity, and tides still followed the moon. Yet beneath that moving surface, the chemistry, the circulation, and the living world within those waters were not quite the same as the oceans we know today. To begin understanding those ancient seas, it helps to remember how old the oceans themselves already were. By the time Colombia existed, Earth's oceans had been present for well over 1 billion years. Rain had fallen, basins had filled, and cycles of evaporation and precipitation had been repeating for ages beyond counting. The oceans were not young, but they were still evolving, shaped continuously by volcanic activity, chemical reactions, and the slow work of living organisms. One of the most important differences lay in the composition of seawater. Today, oxygen is abundant in the upper layers of the ocean, allowing fish, crustaceans, and countless other animals to thrive. During the time of Colombia, oxygen was increasing, but it had not yet reached modern levels, especially in deeper waters. Many parts of the ocean may have remained low in oxygen, or even anoxic, meaning almost entirely without it. This had significant consequences for chemistry, Iron, which today tends to oxidize quickly in the presence of oxygen, could remain dissolved in seawater under low oxygen conditions. Rivers carried iron from weathered rocks into the sea, and underwater volcanic activity added more. In some regions, this dissolved iron accumulated in large quantities. Then, in shallow waters where photosynthetic microorganisms released oxygen, chemical reactions caused the iron to precipitate, forming tiny particles of iron oxide that settled slowly to the sea floor. Over immense spans of time, these particles formed layered deposits, alternating with silica and other minerals, creating the banded iron formations that geologists study today. These formations are more than just mineral resources. They're records of ancient ocean chemistry, quiet evidence of a time when the oceans carried far more dissolved iron than they do now, and when the balance between oxygen and other elements was still shifting. If you had been able to look into those waters, the colour might sometimes have been slightly different from modern seas. In certain conditions, high concentrations of microorganisms or suspended minerals can give water greenish or brownish tints. Shallow coastal waters, especially, may have appeared more opaque, carrying sediments from rivers and microbial communities growing in the sunlight. The surface of the ocean, however, would still have reflected the sky, moving with the wind in patterns that would feel familiar to anyone who has ever watched waves rolling toward a shore. Storms formed then as they do now, driven by temperature differences and atmospheric circulation. Winds gathered strength across open water, building waves that crashed against rocky coasts. The absence of large marine animals would have changed the character of those waters in subtle ways. There were no fish breaking the surface, no seabirds diving, no whales exhaling mist into the air. The surface might often have seemed calm and undisturbed, except for wind and weather, yet the oceans were far from empty. Microbial life was abundant, forming the foundation of ecosystems that operated on a microscopic scale but spanned vast areas. Cyanobacteria in particular played a crucial role. These organisms use sunlight to produce energy, releasing oxygen as a byproduct. Over millions of years, their activity slowly transformed both the oceans and the atmosphere. In shallow regions, microbial mats could cover the sea floor, forming layered structures as sediments became trapped within growing colonies. These mats were not passive films, but active communities, processing nutrients, exchanging gases, and influencing the formation of minerals. Some of these environments were so stable that layers accumulated year after year, preserving delicate textures that can still be seen in ancient rocks. Ripple marks from currents, tiny cracks formed as sediments dried and re-wetted, and thin laminae created by microbial growth all provide glimpses into these quiet, ancient shorelines. Farther from land, the open ocean would have been vast and deep, its surface stirred by winds, its depths dark and cold. Circulation patterns, driven by temperature differences and the rotation of the planet, would have moved water across great distances. Warm surface waters flowed toward cooler regions, cooled and sank, while deeper waters gradually rose elsewhere, completing slow, global cycles. These circulation patterns were influenced by the arrangement of continents. Colombia, as a large landmass, would have affected ocean currents, redirecting flows and shaping climate. Currents carry heat from equatorial regions toward higher latitudes, and changes in continental positions can alter these pathways, sometimes leading to warmer or cooler climates in different parts of the world. Tides also played a role in shaping coastal environments. With the moon closer to Earth than it is today, tidal forces were somewhat stronger. Along shallow coastlines, this may have created broad tidal flats exposed at low tide and submerged again hours later. These flats were ideal environments for microbial communities, as periodic exposure to air and sunlight created conditions favourable for photosynthesis. The rhythm of the tides, the steady rise and fall of water, would have been one of the most noticeable cycles in that ancient world. Day and night passed a little more quickly, and the tides followed their own pattern, governed by the moon's orbit. These cycles repeated endlessly, long before any creature existed to measure them or give them names. Beneath the surface, hydrothermal vents provided another kind of environment entirely. Along mid-ocean ridges, where tectonic plates were pulling apart, seawater seeped into cracks in the crust, was heated by magma, and then rose back to the seafloor, carrying dissolved minerals. These vents created localized regions rich in chemical energy, supporting microbial communities that did not rely on sunlight at all. Life near these vents used chemical reactions, rather than photosynthesis, to obtain energy, a process known as chemosynthesis. Even today, such ecosystems exist in the deep ocean, populated by specialized organisms. During the time of Colombia, similar environments may have been widespread, offering niches where life could thrive even in total darkness. Volcanic activity beneath the oceans also influenced their chemistry. Submarine eruptions released gases and minerals, altering the composition of seawater locally and sometimes on a broader scale. Lava flows spread across the sea floor, creating new crust that gradually moved away from spreading centres. This constant creation and recycling of oceanic crust meant that the ocean basins themselves were always changing, though very slowly. New crust formed, older crust was subducted, and sediments accumulated on the seafloor, recording changes in climate, chemistry, and biological activity. The sediments themselves were often fine-grained, settling slowly through the water column. In the absence of burrowing animals, these layers could remain undisturbed, preserving delicate structures that modern geologists can still study. Thin laminations, sometimes only fractions of a millimetre thick, record seasonal or annual variations, offering rare glimpses into the rhythms of ancient environments. Temperature differences in the oceans may also have been more pronounced in some regions. With different atmospheric compositions and continental arrangements, patterns of heat distribution could vary from those of today. Yet the basic physics of water, its capacity to store heat, its movement driven by density differences, ensured that the oceans remained a stabilizing influence on climate. Without the moderating effect of oceans, Earth's temperature would fluctuate far more dramatically between day and night, between seasons. Even in the Paleo-proterozoic, the oceans played this buffering role, absorbing heat during warm periods and releasing it slowly over time. Storms over the ocean would have looked familiar, towering clouds rising where warm, moist air met cooler layers above. Lightning flashed, rain fell in sheets, and winds churned the surface into white-capped waves. The energy driving these storms was the same then as now. Sunlight heating the surface, water evaporating, air rising and cooling. After the storms passed, the surface would calm again, waves settling into long swells that travelled across great distances, carrying energy from far-off weather systems to distant shores. Another aspect of these ancient oceans that is easy to overlook is their role in shaping the continents themselves. Waves eroded coastlines, breaking rock into smaller fragments. Currents carried sediments along shores, depositing sand in some areas and removing it in others. Over millions of years, these processes altered the shape of the land, carving cliffs, forming beaches, and building deltas where rivers met the sea. In some regions, shallow seas may have extended far inland, covering large areas of the continent during periods of higher sea level. These inland seas provided environments where sediments accumulated and microbial life flourished. When sea levels fell again, these areas were exposed, leaving behind layers of limestone and other sedimentary rocks. Sea level itself was influenced by many factors, including tectonic activity, climate, and the volume of water stored in glaciers. During warmer periods, higher sea levels flooded coastal regions. During cooler periods, more water was locked in ice, and shorelines moved outward. These changes unfolded slowly over thousands or millions of years, yet they reshaped vast areas of the planet. If you imagine standing on a high cliff overlooking the ocean during the time of Colombia, the view would be both familiar and strange. Waves would break against the rocks below. Clouds would drift across the sky. The horizon would stretch unbroken as it does today. But the water below would contain none of the creatures we associate with the sea. No schools of fish, no coral reefs, no drifting jellyfish. Only microorganisms, invisible to the eye, carrying out processes that would gradually change the planet. There is something quietly remarkable about that thought. The transformation of Earth's atmosphere, the rise of oxygen, and the eventual evolution of complex life all depended on these microscopic organisms working in oceans that, to a casual observer, might have seemed empty. The oceans of the Paleo-proterozoic world were not silent in a physical sense. Waves crashed, winds howled, storms raged. But biologically they were quieter, lacking the sounds and movements of larger animals. The activity was there, immense and vital, but it was taking place on scales too small to see. And as the continents of Colombia continued their slow movements, the oceans responded, currents shifting, basins opening and closing, coastlines advancing and retreating. Land and sea were part of the same system, each shaping the other in ways that would only become fully visible over immense stretches of time. If you could stand on the surface of Earth during the time of Colombia and take a slow breath, the first sensation would be unfamiliarity. The air would still move with the wind, still carry the scents of minerals, salt and distant rain, but its composition would be different enough that breathing it comfortably would be difficult for a modern human. Oxygen was present, but in smaller amounts than today, and other gases, some more common then than now, shaped both the climate and the chemistry of the planet in subtle but important ways. To understand that ancient atmosphere, it helps to remember that Earth's air has never been fixed or permanent. It has changed continuously over billions of years, shaped by volcanoes, oceans, sunlight and living organisms. The atmosphere during Columbia's time was not the first atmosphere the planet had known, nor would it be the last. It was one stage in a long, gradual transformation. Far back in Earth's history, the atmosphere contained almost no oxygen at all. Instead, it was dominated by gases released from the planet's interior: carbon dioxide, water vapour, nitrogen, methane, and smaller amounts of other compounds. Volcanoes played a major role in supplying these gases, releasing them through eruptions and through quieter processes such as fumaroles and hydrothermal vents. By the time Colombia existed, something remarkable had already begun to change the air. For hundreds of millions of years, cyanobacteria in the oceans had been producing oxygen as a byproduct of photosynthesis. At first, that oxygen did not accumulate in the atmosphere because it reacted with dissolved iron and other elements in the oceans, becoming locked into minerals. Only after those chemical sinks were gradually filled did oxygen begin to build up in the air. This transition, often called the Great Oxidation Event, had started long before Colombia assembled, but its effects were still unfolding during that era. Oxygen levels were rising slowly, though they were still far below modern concentrations. Estimates vary, but many scientists believe that oxygen may have been only a few percent of the atmosphere, compared to about 21% today. Breathing such air would feel different. The body depends on oxygen to release energy from food, and lower concentrations mean less efficient respiration. At high altitudes on modern Earth, where oxygen levels are reduced, people often feel short of breath or fatigued. The atmosphere of Columbia's time might have felt somewhat like that, though the exact experience would depend on many factors, including total air pressure and the presence of other gases. Nitrogen, which makes up most of today's atmosphere, was already abundant and probably formed the bulk of the air then as well. Nitrogen is relatively inert, neither strongly reactive nor harmful in itself, and it acts as a kind of background gas, diluting oxygen and influencing atmospheric pressure. Carbon dioxide was likely more abundant than today, though estimates again vary. This gas plays an important role in regulating climate by trapping heat, and higher concentrations may have helped keep the planet warm despite the sun being slightly dimmer than it is now. Without sufficient greenhouse gases, Earth might have frozen over because the young sun emitted less energy than it does today. Methane may also have been present in significant amounts, produced by certain microorganisms in oxygen-poor environments. Methane is a powerful greenhouse gas, and its presence could have contributed to warming the atmosphere. However, methane is unstable in the presence of oxygen, so as oxygen levels increased, methane concentrations may have declined. The balance between these gases created an atmosphere that was not toxic in the sense of being filled with lethal poisons, but it was certainly alien compared to what we're used to breathing. The chemistry of the air influenced everything from the colour of the sky to the rate at which rocks weathered. The sky itself may have appeared slightly different. The blue colour we see today results from the scattering of sunlight by molecules in the atmosphere, particularly nitrogen and oxygen, with different proportions of gases and possibly more airborne particles from volcanic activity. The hue of the sky might have been subtly altered, perhaps paler or hazier in some regions. Sunsets could have been especially striking. Particles in the atmosphere scatter shorter wavelengths of light, allowing reds and oranges to dominate near the horizon. If volcanic ash or other aerosols were more common, sunsets might have displayed deep, vivid colours, lingering long after the sun dipped below the horizon. Clouds, however, would have looked much the same. Water vapour condenses into droplets regardless of the precise composition of the atmosphere, and the familiar shapes of cumulus and stratus clouds would have drifted across the sky as they do now. Rain would fall, evaporate and fall again, part of a cycle that has operated on Earth for billions of years. Weather systems during the time of Colombia were driven by the same fundamental processes that shape weather today. Uneven heating of the planet's surface created pressure differences, setting air in motion. Warm air rose, cooled and formed clouds. Storms developed where conditions were right, releasing rain and sometimes lightning. Lightning itself may have been particularly important in that ancient world. Electrical discharges in the atmosphere can drive chemical reactions, producing compounds that eventually settle to the surface. Some scientists believe that lightning played a role in shaping the chemistry of early environments, long before complex life evolved. Volcanoes also influenced the atmosphere in powerful ways. Large eruptions released ash and gases into the air, sometimes affecting climate on regional or even global scales. Sulfur dioxide, for example, can form aerosols that reflect sunlight, temporarily cooling the planet. Over longer periods, volcanic emissions of carbon dioxide contributed to warming. During the time of Colombia, volcanic activity was likely more intense in some regions than it is today, partly because the planet's interior was still losing heat more rapidly. Chains of volcanoes along subduction zones and rift systems would have released steady streams of gases, subtly altering atmospheric composition over millions of years. The interaction between atmosphere and land was also different in the absence of plants. Today, forests and grasslands play a major role in regulating carbon dioxide levels, absorbing the gas during photosynthesis and storing carbon in wood and soil. During Columbia's time, this role was performed mainly by microorganisms in the oceans and by chemical weathering of rocks. When rain falls, it dissolves a small amount of carbon dioxide, forming a weak acid that reacts with minerals in rocks. This process, called chemical weathering, removes carbon dioxide from the atmosphere over long time scales, eventually locking it into carbonate rocks. Even in the ancient world, this slow process helped regulate climate, balancing volcanic emissions over millions of years. Another difference in that atmosphere was the absence of an ozone layer as thick as the one we have today. Ozone forms from oxygen in the upper atmosphere, absorbing much of the sun's harmful ultraviolet radiation. With lower oxygen levels, the ozone layer would have been thinner, allowing more ultraviolet light to reach the surface. This increased radiation was one reason why early life thrived mainly in water, where even a few centimetres of depth provided protection. Microbial mats in shallow water or damp environments were exposed to sunlight but still shielded from the most intense radiation. The smell of the air, if one could notice it, might have been faintly different as well. Volcanic regions can release gases like sulfur dioxide and hydrogen sulfide, giving the air a sharp or slightly bitter scent. Coastal areas influenced by microbial activity might carry subtle odours unfamiliar to modern noses. At night, the atmosphere would cool, and in the absence of artificial light, the sky would darken to a depth rarely seen today. Stars would shine with extraordinary clarity, and the Milky Way would stretch across the sky as a bright band. The moon, closer than it is now, would appear slightly larger, casting stronger light on the landscape below. The rhythm of day and night, the cycling of temperature, the movement of winds, all continued as they always had. Yet the details were different enough to make the experience of that world feel quietly unfamiliar. Over long spans of time, the atmosphere was not static. Oxygen levels continued to rise slowly, influenced by the balance between production by photosynthetic organisms and consumption by chemical reactions and respiration. Changes in volcanic activity, continental positions, and ocean chemistry all played roles in shaping the composition of the air. Climate, too, responded to these changes. Periods of relative warmth alternated with cooler intervals. Evidence from ancient rocks suggests that glaciations occurred at various times, indicating that the atmosphere's greenhouse effect varied over geological time. These changes did not happen quickly. They unfolded over millions of years, far too slowly for any single generation of organisms to notice, yet steadily enough to shape the long-term evolution of life. One of the most remarkable aspects of this ancient atmosphere is that it was being transformed by life itself. The oxygen we breathe today is, in a sense, the accumulated waste product of countless microorganisms that lived and died over billions of years. The air is not merely a backdrop to life, but one of its creations. During the time of Colombia, that transformation was still in progress. The atmosphere was in transition, no longer the oxygen-poor air of the earliest Earth, but not yet the oxygen-rich air that would support complex animals. Standing in that world, if such a thing were possible, you might feel the wind against your skin, hear the distant rumble of surf, see clouds drifting overhead, and yet sense that something was different in ways difficult to define. The air would feel thinner in oxygen, the sunlight slightly harsher, the land and sea shaped by processes both familiar and ancient. It is a reminder that the environment we know today is not the only one Earth has ever known. The planet has worn many atmospheres, just as it has worn many continents and oceans. Each stage set the conditions for the next, guiding the course of geological and biological history. Thinking about climate during the time of Colombia requires a small shift in perspective, because it is easy to imagine ancient Earth as either uniformly hot or uniformly hostile. In reality, the climate of that distant era was complex, shaped by many of the same forces that influence weather and temperature today: sunlight, atmospheric composition, the arrangement of continents, volcanic activity, and the slow circulation of the oceans. The difference was not that these processes were absent, but that their balance was different, creating conditions that would feel unfamiliar in subtle but important ways. To begin with, the sun itself was slightly dimmer. About 1.8 billion years ago, solar output was roughly 10% lower than it is today. That might not sound like a large difference, but on a planetary scale, it is significant. Less incoming energy would normally mean a colder Earth, perhaps even one locked in ice. Yet geological evidence shows that the planet was not frozen over during most of Colombia's existence. Liquid oceans were widespread, rivers flowed, and life continued to thrive in marine environments. This apparent contradiction is sometimes called the faint young sun paradox. The explanation most scientists favour involves greenhouse gases in the atmosphere, particularly carbon dioxide and methane, which trapped heat and compensated for the weaker sunlight. In effect, the atmosphere acted as a blanket, allowing the planet to maintain temperatures suitable for liquid water. Carbon dioxide levels were likely higher than they are today, though estimates vary depending on the evidence examined. Volcanic eruptions released carbon dioxide continuously, and without large land plants to remove it rapidly, more of the gas remained in the air. Methane, produced by microorganisms in oxygen-poor environments, may also have contributed to warming, especially in certain periods. These gases helped maintain a climate that was generally warm enough to prevent global freezing, but that does not mean the planet was uniformly hot. Climate varied from region to region, influenced by latitude, altitude, and proximity to the oceans. Coastal areas moderated by water may have experienced relatively stable temperatures, while continental interiors, far from the influence of the sea, could have undergone greater swings between day and night or between seasons. The arrangement of Colombia itself played an important role in shaping climate. Large landmasses affect atmospheric circulation by heating and cooling differently than oceans. During the day, land warms more quickly than water, creating pressure differences that drive winds. At night, land cools more rapidly, reversing some of these patterns. On a continental scale, these differences can influence monsoon-like systems, rainfall distribution, and prevailing wind directions. With a supercontinent as large as Colombia, some regions deep in the interior may have been relatively dry. Moisture carried from the oceans would gradually fall as rain along coastal regions and mountain ranges, leaving less to reach the far interior. This pattern is seen even today in large continents, where central deserts often form in rain shadows or far from oceanic moisture. At the same time, other areas of Colombia may have experienced significant rainfall, especially near coastlines or in regions where prevailing winds carried moist air inland. Rivers flowing from these regions would have transported sediments toward the sea, shaping floodplains and deltas over long periods. Seasonal changes also existed, though their intensity depended on latitude and the tilt of Earth's axis, which has remained relatively stable over geological time. Regions closer to the equator would have experienced more consistent temperatures, while higher latitudes saw greater variation between warmer and cooler periods of the year. There is evidence that glaciers formed during parts of the Paleo-proterozoic, indicating that cooler intervals occurred. Rocks showing signs of glacial activity, such as striations carved by moving ice and deposits left behind by melting glaciers, have been found in several regions. These findings suggest that Earth's climate during Columbia's time was not static but fluctuated, sometimes shifting toward colder conditions. The causes of these cooler periods are still studied, but several factors may have contributed. Changes in atmospheric composition, variations in volcanic activity, and the positioning of continents relative to the poles could all influence global temperature. When large land masses drift toward higher latitudes, snow and ice can accumulate more easily, reflecting sunlight and reinforcing cooling in a feedback process. Volcanic eruptions also played a role in climate. In the short term, large eruptions can cool the planet by injecting ash and sulfur-rich aerosols into the atmosphere, reflecting sunlight back into space. Over longer periods, however, volcanic emissions of carbon dioxide tend to warm the climate. The balance between these effects depends on the scale and frequency of eruptions, as well as on the planet's capacity to remove carbon dioxide through weathering and other processes. Weathering itself was an important part of the climate system. When rainwater reacts with rocks, it removes carbon dioxide from the atmosphere and locks it into minerals. This process acts as a long-term thermostat, gradually reducing greenhouse gases when temperatures are high and slowing down when temperatures fall. Even during the time of Colombia, this slow chemical cycle helped stabilize the climate over millions of years. Another factor influencing climate was the circulation of the oceans. Ocean currents transport heat around the planet, carrying warm water toward cooler regions and helping moderate temperature differences. The configuration of continents determines the pathways available for these currents. With Colombia arranged differently from modern continents, ocean circulation patterns would also have been different, altering regional climates in ways that are still being studied through modelling and geological evidence. Storm systems during this era were likely familiar in many respects. Warm air rising over oceans would form clouds, releasing rain as it cooled. Thunderstorms would develop in regions with sufficient moisture and temperature contrast. Winds driven by pressure differences would sweep across plains and coastlines, shaping dunes and transporting dust. The absence of vegetation, however, may have influenced local climates in noticeable ways. Plants today play a significant role in regulating temperature and humidity by releasing water vapour through transpiration and by shading the ground. Without forests or grasslands, the land surface of Colombia would have absorbed and radiated heat differently, possibly leading to greater temperature swings between day and night in some regions. Dust in the atmosphere may also have been more common, particularly in arid areas where loose sediments could be lifted by the wind. Dust particles influence climate by reflecting sunlight and by acting as nuclei around which cloud droplets can form. Large dust storms, if they occurred, might have affected regional weather patterns for days or weeks at a time. The length of the day also had subtle climatic implications. With Earth rotating more quickly, days were shorter, meaning the cycle of heating and cooling occurred more rapidly. This would not necessarily change average temperatures dramatically, but it could influence atmospheric circulation and the timing of daily weather patterns. Another element worth considering is the role of ice, not just in glaciers but in seasonal snow cover. When snow accumulates, it reflects a large portion of incoming sunlight, cooling the surface. Changes in snow and ice coverage can therefore amplify climate shifts. Evidence from ancient rocks suggests that ice sheets did exist in certain regions during parts of this era, indicating that polar or high-altitude environments experienced sustained cold conditions. Despite these variations, the overall climate of the age of Colombia appears to have been relatively stable on the longest timescales. There is no evidence of extreme global freezing during most of its existence, nor of runaway greenhouse conditions that would have rendered the oceans inhospitable. Instead, the planet maintained conditions that allowed microbial life to flourish and slowly transform the atmosphere. Rainfall patterns would have varied widely across the continent. Some regions may have received frequent rains, feeding rivers that carried sediments to the sea. Other areas, especially those shielded by mountains or far from oceanic moisture, may have been dry for long periods, their surfaces shaped more by wind than by water. In those dry regions, temperature differences between day and night could have been significant. Without vegetation or thick soils to retain heat, the land would warm quickly under the sun and cool rapidly after sunset. The air might feel warm during the day and noticeably cooler at night, a pattern still seen in modern deserts. Near the coasts, the influence of the ocean moderated these swings. Water warms and cools more slowly than land, creating more stable temperatures. Sea breezes would develop as warm air rose over land, and cooler air moved in from the ocean, bringing moisture and sometimes clouds. The rhythm of climate, the alternation of warm and cool periods, wet and dry seasons, storms and calm intervals, would have unfolded continuously, shaping the land and influencing the chemistry of the oceans and atmosphere. Though the details differed from modern conditions, the fundamental processes were the same. Energy from the sun driving circulation in air and water, gravity pulling rain to the surface, and heat flowing from the planet's interior toward the crust. It is easy to imagine climate as something dramatic, a sudden storm or a rapid shift in temperature, but much of Earth's climate history is written in slow changes, gradual shifts that become visible only when viewed over millions of years. Layers of sediment accumulate, isotopes in minerals record temperatures, and patterns of erosion reveal long-term trends. By studying these records, scientists can reconstruct the climate of Colombia's time, not in the sense of knowing the weather on a particular day, but in understanding the broad patterns that shape the planet over immense spans of time. Standing in that ancient world, if one could, you might feel the warmth of the sun, notice clouds drifting overhead, and hear the distant sound of wind moving across bare rock. The air would feel different, the land unfamiliar, but the fundamental experience of weather, the passing of clouds, the smell of rain, the cooling of evening would still be recognizable. Looking across the land and seas of Earth during the time of Columbia, the most important living things on the planet would have been almost impossible to see. There were no animals roaming the land, no forests rising toward the sky, no fish moving in schools beneath the waves. Life was everywhere, but it existed at a scale so small that an entire thriving ecosystem could rest on the surface of a rock or drift unnoticed in a drop of water. It is easy, from a modern perspective, to think of a world without visible plants or animals as empty, but that would not be accurate at all. The planet during this era was alive in ways that were subtle yet immensely powerful. Microorganisms dominated every environment where conditions allowed, shaping the chemistry of oceans, sediments, and even the atmosphere itself. By the time Columbia existed, life had already been present on Earth for well over 1 billion years. The earliest known fossils of microorganisms date back more than 3.5 billion years, meaning that microbial life had a long history before the supercontinent formed. Over that immense span of time, evolution had already produced a remarkable diversity of bacteria and archaea, organisms capable of surviving in environments ranging from sunlit shallows to dark, mineral-rich hydrothermal vents. Cyanobacteria were among the most important of these organisms. They carried out photosynthesis, using sunlight to convert carbon dioxide and water into organic matter, releasing oxygen as a byproduct. This process, repeated countless times across oceans and shallow seas, gradually altered the composition of the atmosphere and the chemistry of the oceans. In shallow marine environments, cyanobacteria often formed microbial mats, layered communities that covered sediments and rocks. These mats were not uniform sheets, but complex ecosystems, with different species occupying different layers depending on their tolerance for light, oxygen, and nutrients. Some layers were dominated by photosynthetic organisms, while others hosted bacteria that thrived in low oxygen or even oxygen-free conditions. Over time, these mats could trap sediments carried by waves and currents. As layers accumulated, they formed structures known as stromatolites, low, rounded mounds composed of alternating layers of microbial material and sediment. Stromatolites grew slowly, sometimes only a few millimeters per year, yet over centuries and millennia they could form substantial structures. Today, stromatolites still exist in a few places, such as Shark Bay in Australia, offering a glimpse of what ancient shorelines may have looked like. During the time of Columbia, however, such structures were far more widespread, common features of shallow coastal waters around the world. If you could walk along a shoreline in that era, you might see broad, flat tidal areas covered with dark, slightly textured surfaces, microbial mats exposed by the retreating tide. They would appear almost like wet leather or thin rubber, glistening in the sunlight. There would be no footprints crossing them, no shells scattered across the sand, only the quiet work of microorganisms absorbing sunlight and processing nutrients. In deeper parts of the ocean, other forms of microbial life dominated. Some organisms lived by consuming organic material sinking from above, while others relied on chemical energy from minerals and gases released by underwater volcanic activity. Around hydrothermal vents, communities of chemosynthetic bacteria thrived, using chemical reactions rather than sunlight to obtain energy. These environments were dark and extreme, yet they supported life that was perfectly adapted to such conditions. Even today, hydrothermal vent ecosystems remind us that life does not depend solely on sunlight. During the time of Columbia, such ecosystems may have been among the most stable and long-lasting habitats on the planet. Another important group of organisms present during this era were early eukaryotes. Unlike bacteria and archaea, which lack internal compartments, eukaryotic cells contain nuclei and other specialized structures. The first eukaryotes had evolved hundreds of millions of years earlier, and by the time of Columbia they were becoming more diverse, though still entirely microscopic. These early eukaryotes represented a significant step in the history of life. Their complex internal organisation allowed for greater specialisation within cells, paving the way, eventually, for multicellular organisms. But during this period, such developments were still in their early stages. Life was complex at the cellular level, but not yet at the level of large bodies or visible forms. The absence of large predators or grazers had profound effects on ecosystems. In modern oceans, microorganisms are constantly consumed by larger organisms, which in turn are eaten by still larger ones. This chain of predation shapes population sizes and nutrient cycles. During the time of Colombia, such food webs were much simpler. Microbes were eaten by other microbes, and organic material was recycled largely within microscopic communities. This simplicity did not mean inefficiency. Microbial ecosystems are remarkably effective at recycling nutrients. Organic matter produced by photosynthetic organisms was broken down by decomposers, releasing nutrients that could be used again. The cycles of carbon, nitrogen, and other elements were already operating, though in forms that differed somewhat from modern systems. One interesting aspect of life in this era is how strongly it influenced the geology of the planet. Microorganisms played a role in the formation of certain minerals, altering the chemistry of sediments and seawater. Some bacteria could precipitate carbonate minerals, contributing to the formation of limestone. Others influenced the deposition of iron and sulfur compounds. In this way, life and geology were closely linked. The activities of microorganisms left traces in rocks that can still be studied today, providing evidence of ancient ecosystems and environmental conditions. The distribution of life was also influenced by environmental factors such as light, temperature, and nutrient availability. In sunlit, shallow waters, photosynthetic organisms dominated. In deeper or darker environments, organisms relying on chemical energy were more common. Temperature gradients near hydrothermal vents or in polar regions created additional ecological niches. Even the land, though largely barren in appearance, may not have been entirely lifeless. Microbial communities can survive in thin films of moisture on rocks, in soils, and in sheltered environments where conditions are suitable. Some of the earliest forms of life may have colonized damp surfaces on land, forming thin crusts that stabilized sediments and influenced weathering processes. These terrestrial microbial communities were likely limited in extent compared to marine ecosystems, but they marked the beginning of life's gradual expansion onto land, a process that would continue over hundreds of millions of years. Time itself would have felt different in such a world, though not in any physical sense, but in the pace of visible change. Without large plants growing season by season, or animals migrating and reproducing, the most obvious changes in the landscape would come from weather and geology rather than from biological activity. Microbial growth is steady but slow from a human perspective. A stromatolite might grow only a few centimetres in a lifetime. A microbial mat might thicken gradually, layer by layer, without any dramatic transformation. Yet over thousands or millions of years, these small changes accumulated, shaping entire environments. The oxygen released by cyanobacteria, for example, did not transform the atmosphere overnight. It built up gradually, over immense spans of time, reacting with minerals, dissolving in oceans, and eventually accumulating in the air. This slow increase in oxygen would eventually make possible the evolution of more complex life, but during the time of Colombia, that process was still underway. It is worth pausing to consider how different the soundscape of such a world would have been. Modern ecosystems are filled with noise, insects buzzing, birds calling, mammals moving through vegetation, waves breaking against reefs alive with organisms. In the age of Colombia, the sounds of life would have been almost non-existent at a human scale. The wind, the waves, the occasional rumble of thunder or distant volcanic activity would dominate the landscape. Life was there, abundant and active, but it operated silently, at microscopic scales. And yet, despite this quietness, The influence of microbes was immense. They were altering the atmosphere, shaping the chemistry of oceans, contributing to the formation of rocks, and preparing the planet for future changes that would eventually lead to the rise of animals and plants. In a sense, they were the engineers of the Earth, though not consciously or deliberately. Their metabolism, their growth, and their interactions with the environment created feedback loops that shaped climate and chemistry over geological time. Looking back, it becomes clear that the age of microbes was not a primitive prelude to more important forms of life. It was a vast and essential chapter in the planet's history, lasting billions of years and laying the foundations for everything that followed. Long before animals breathed, before forests covered the land, and before the sky held the familiar balance of gases we depend on today, the atmosphere of Earth was being reshaped by processes so gradual that no single generation of organisms could ever have noticed them. The transformation did not arrive suddenly, and it was not dramatic in the way a volcanic eruption or a meteor impact might be. Instead, it unfolded in a steady, patient way, one molecule at a time, guided by the quiet labour of microorganisms living in oceans and shallow waters across the planet. This transformation is often called the oxygen revolution, though the word revolution can give the wrong impression. It was not fast, not violent, and not even particularly noticeable on short timescales. It was a slow turning of the planet's chemistry, taking place over hundreds of millions of years, beginning long before the time of Columbia and continuing throughout its existence. To understand why this change mattered so much, it helps to imagine Earth before oxygen became abundant. For most of the planet's early history, the atmosphere contained very little free oxygen. Volcanoes released gases such as carbon dioxide, water vapour, nitrogen, methane, and ammonia. Oceans were rich in dissolved iron and other elements that reacted quickly with any oxygen that appeared. Even if oxygen was produced, it rarely remained free for long. It was captured almost immediately by chemical reactions, disappearing into minerals or combining with other substances. Then came cyanobacteria, tiny organisms capable of photosynthesis. Using sunlight, they split water molecules, releasing oxygen as a byproduct. At first, this oxygen reacted with iron in the oceans, forming iron oxides that settled to the seafloor. Over immense spans of time, these reactions produced vast deposits of banded iron formations, layer upon layer of iron-rich rock that still exist today. Those rocks are a kind of quiet record of the early oxygen cycle. Each thin layer represents a period when oxygen was produced, reacted and locked away, preventing it from building up in the atmosphere. The oceans, in a sense, were acting as a vast chemical sink, absorbing the oxygen released by microorganisms. But the capacity of that sink was not infinite. Eventually, after countless generations of cyanobacteria had lived and died, much of the dissolved iron had been oxidized. The oceans could no longer absorb oxygen at the same rate, and gradually, slowly, oxygen began to accumulate in the atmosphere. This change did not happen evenly or all at once. Oxygen levels likely rose and fell over long periods, influenced by volcanic activity, ocean chemistry, and the distribution of microbial communities. Some intervals may have seen higher concentrations, followed by declines when chemical reactions consumed oxygen faster than it was produced. By the time Colombia existed, oxygen was present in the atmosphere in measurable amounts, though still far below modern levels. Estimates suggest it may have reached a few percent of the atmosphere, enough to begin influencing climate and chemistry in new ways, but not yet enough to support complex animals. One of the most important consequences of rising oxygen was the formation of the ozone layer. Ozone forms when ultraviolet radiation from the sun splits oxygen molecules, allowing individual oxygen atoms to recombine into 3-atom ozone molecules. These molecules absorb much of the sun's harmful ultraviolet radiation, protecting life at the surface. Before oxygen became abundant, ultraviolet radiation reached the surface more easily, making shallow water or protective environments more favourable for life. As oxygen levels rose and ozone formed, the surface of the planet gradually became less hostile to organisms exposed to sunlight. This change would eventually allow life to expand into new habitats, though that transition still lay far in the future during the time of Colombia. Oxygen also affected the chemistry of rocks and soils. When oxygen reacts with minerals, it often produces oxides, giving rocks reddish or brownish colours. The appearance of red beds, sedimentary rocks stained with iron oxides, is one of the geological signs that oxygen had become more common in the atmosphere. These rocks provide another line of evidence for the gradual transformation of the air. The rise of oxygen was not entirely beneficial to all forms of life. For many early microorganisms, oxygen was toxic. These organisms had evolved in environments where oxygen was scarce, and exposure to it could damage cellular structures. As oxygen levels increased, some species retreated to low oxygen environments, such as deep sediments, stagnant waters, or hydrothermal systems where oxygen remained limited. Others adapted, evolving mechanisms to tolerate or even use oxygen in their metabolism. Oxygen-based respiration is far more efficient than many earlier metabolic processes, allowing organisms to extract more energy from the same amount of food. This increased efficiency would later support the evolution of larger and more complex organisms, though during the time of Colombia, such developments were still distant. Another subtle effect of rising oxygen involved methane. Methane is a powerful greenhouse gas, and in an atmosphere with little oxygen, it can accumulate to significant levels, but oxygen reacts with methane, breaking it down. As oxygen increased, methane concentrations likely declined, which may have contributed to periods of cooling in Earth's climate. This interplay between gases, oxygen rising, methane falling, carbon dioxide fluctuating, created a dynamic atmosphere, constantly adjusting to the balance of biological and geological processes. The oceans too were changing. Oxygen produced in surface waters gradually diffused into deeper layers, though this process was slow and uneven. Some regions of the deep ocean may have remained low in oxygen for long periods, while others experienced gradual increases. This patchwork of conditions influenced the distribution of microbial life and the chemistry of sediments. Evidence from ancient rock suggests that oxygenation of the oceans occurred in stages, rather than as a single global event. Shallow waters near active photosynthetic communities may have become oxygen-rich first, while deeper basins lagged behind. Over time, these oxygenated zones expanded, altering ecosystems and chemical cycles. It is remarkable to consider how small organisms, each measuring only micrometers across, could reshape an entire planet. No single cyanobacterium had any awareness of the larger transformation taking place. Each cell simply carried out its metabolism, capturing sunlight and releasing oxygen, generation after generation, over spans of time so vast that mountains rose and eroded while the process continued. The scale of this change is difficult to grasp. The oxygen in the atmosphere today, every breath taken by animals, every flame that burns, every rusting surface, traces its origins back to these ancient microbial processes. During the time of Colombia, the oxygen revolution was still underway, not yet complete, but already far advanced compared to earlier eras. The atmosphere was becoming more oxidizing, the oceans gradually changing, and the stage was being set for evolutionary developments that would unfold hundreds of millions of years later. Another consequence of rising oxygen was its effect on weathering and nutrient cycles. Oxygen allows certain chemical reactions to occur more readily, influencing the breakdown of rocks and the release of nutrients into soils and waters. These nutrients, in turn, supported microbial growth, creating feedback loops that linked geology, chemistry, and biology. The land itself began to reflect these changes. Soils, though still thin and largely inorganic compared to modern soils, were influenced by oxidation reactions. Minerals altered in the presence of oxygen produced new compounds, changing the colour and texture of sediments. The atmosphere, oceans and land were part of a single interconnected system, each influencing the others in ways that were often subtle but profound over long timescales. It is interesting to think about how gradual this transformation must have seemed, even from a geological perspective. There was no moment when the sky suddenly changed colour, no day when the air abruptly became breathable for complex life. Instead, oxygen levels crept upward, fraction by fraction, century by century, millennium by millennium. If one could measure the atmosphere year by year, the change would have been imperceptible. Only by comparing rocks separated by tens or hundreds of millions of years does the trend become clear. And yet, this slow revolution was one of the most important events in Earth's history. Without it, complex life as we know it would never have evolved. Oxygen made possible new forms of metabolism, new ecological interactions, and eventually the emergence of multicellular organisms. During the Age of Columbia, these future developments were still distant, but the foundation was already being laid. The air was changing, the seas were changing, and life was adapting to conditions that were gradually becoming more favourable for complexity. Standing in that ancient world, if such a thing were possible, you might not notice anything dramatic in the air around you. The wind would still move across the land, clouds would still drift overhead, and rain would still fall. The transformation of the atmosphere was invisible to the senses, unfolding quietly in the background of the planet's daily rhythms, and that quietness is part of what makes the story so remarkable. The greatest changes in Earth's history are not always the loudest or the fastest. Sometimes they are the slowest, the ones that unfold over spans of time so vast that they can only be seen in hindsight, written in layers of rock and in the chemistry of minerals. Another difference in the world of Colombia that's easy to overlook at first but becomes quietly fascinating once you think about it is the rhythm of time itself. The planet was still turning, the sun was still rising and setting, the moon was still moving across the sky, but the timing of these cycles was not quite what we're used to today. A day was shorter, the moon was closer, and the tides that followed its pull moved with a slightly different strength and tempo than the ones we see now. To understand why this was the case, it helps to remember that Earth and the Moon have never been completely separate in their evolution. From the very beginning, they have been part of a connected system, interacting through gravity in ways that slowly but steadily change both bodies over immense spans of time. The most important process in this relationship is tidal friction. The Moon's gravity pulls on Earth's oceans, raising tidal bulges on the side facing the Moon, and the side facing away from it. Because Earth rotates, these bulges are not perfectly aligned with the Moon. They are dragged slightly ahead by the spinning planet, and this creates a gravitational interaction that transfers a tiny amount of Earth's rotational energy to the Moon. The result is gradual but measurable. Earth's rotation slows down very slightly, making days longer over time, and the Moon moves farther away, drifting outward by a few centimetres each year. It is a small change, almost impossible to notice in a human lifetime, but over hundreds of millions or billions of years, it adds up to a significant difference. During the time of Columbia, roughly 1.8 to 1.5 billion years ago, the day may have been only about 18 or 19 hours long. The exact length is still studied, and estimates vary depending on the methods used, but there is strong evidence from geological records that Earth's rotation was indeed faster. Some of this evidence comes from ancient tidal deposits. In certain sedimentary rocks, particularly those formed in shallow coastal environments, layers can record daily, monthly, and seasonal cycles. These patterns, preserved in fine laminations, sometimes reveal how many days there were in a month or a year at the time the sediments were deposited. By studying these ancient rhythms, scientists have been able to estimate how Earth's rotation has changed over time. The results suggest that days were significantly shorter in the distant past, gradually lengthening as tidal friction slowed the planet's spin. What would a shorter day have felt like? Sunrise and sunset would come sooner, of course. but not in a way that would necessarily feel rushed. The cycle of light and darkness would still feel natural, because life evolves in step with its environment. If complex organisms had existed then, their internal clocks would have adapted to the shorter rhythm, just as ours are adapted to a 24-hour day. Temperature patterns might also have been slightly different. With less time for the sun to heat the surface during the day, and less time for cooling at night, the daily temperature swings in some regions might have been moderated, though many other factors, such as atmospheric composition and cloud cover, would also influence these patterns. The moon itself, meanwhile, would have appeared noticeably larger in the sky. Not dramatically so, but enough that careful observers would have seen a difference. Being closer to Earth, the moon would have exerted a somewhat stronger gravitational pull, influencing tides more strongly than it does today. Tides are among the most visible effects of the Earth-Moon system. The rise and fall of sea level along coastlines is driven primarily by the moon's gravity, with the sun contributing a secondary effect. When the moon was closer, the tidal range in many places may have been greater, especially in shallow coastal regions where the shape of the coastline amplifies tidal motion. Imagine standing on a broad tidal flat during that era. The water slowly retreats, exposing a wide expanse of wet sediment, perhaps dotted with low stromatolite mounds and thin microbial mats glistening in the sunlight. Hours later, the tide returns, advancing steadily across the flat, covering the surface once again. These tidal cycles were not just a physical phenomenon but an important ecological rhythm. In shallow waters, periodic exposure to air and sunlight created environments where microbial communities could thrive. The alternation between submerged and exposed conditions influenced nutrient exchange, temperature, and light availability. Over time, tides also shaped the coastline itself. Waves and currents moved sediments, carved channels, and built up bars and deltas. In some places, tidal currents may have been strong enough to leave distinctive ripple patterns in the sediment, patterns that hardened into rock and remain visible today, providing clues to ancient tidal environments. The moon's proximity also affected the rate at which Earth's rotation slowed. Tidal friction is more effective when the moon is closer, so in earlier eras, the lengthening of the day may have occurred more rapidly than it does now. Over billions of years, this gradual breaking has transformed Earth's rotation from what may once have been a day of only a few hours to the 24-hour cycle we experience today. It is a reminder that even something as seemingly constant as the length of a day is not fixed forever. The rhythms we take for granted are part of a long, evolving system, shaped by gravitational interactions that operate quietly but persistently. The night sky during the time of Columbia would have been both familiar and subtly different. The stars themselves would have been arranged much as they are now, though the constellations would not yet have been named or imagined by human minds. The Milky Way would have stretched across the sky, bright and detailed in the absence of artificial light. The moon, slightly larger, would have dominated the night, its phases marking time in a steady cycle. The shorter day meant that the apparent motion of the moon across the sky would have been somewhat different in timing, but its patterns would still have been recognizable, waxing and waning in a rhythm that has remained unchanged in its basic form for billions of years. Lunar eclipses and solar eclipses would also have occurred, governed by the same orbital mechanics that produce them today. With the moon closer, total solar eclipses may have been slightly more common, or lasted a little longer, as the moon would have covered the sun more completely. Another subtle effect of a faster rotation involves the atmosphere and oceans. The rotation of the planet influences the Coriolis effect, which affects the paths of winds and ocean currents. A faster rotation strengthens this effect, potentially altering large-scale circulation patterns in the atmosphere and oceans. This does not mean that storms or currents were dramatically different in appearance, but the underlying dynamic shaping weather and climate may have followed somewhat different patterns, influencing the distribution of heat and moisture across the planet. The closer moon also meant that tidal forces acting on the solid Earth itself were slightly stronger. The crust experiences tiny deformations as it responds to gravitational pulls, rising and falling by small amounts. These effects are subtle, but over geological time they contribute to the dissipation of energy and the gradual evolution of the Earth-Moon system. It is interesting to reflect on how these slow changes connect the present to the distant past. The length of our day, the size of the moon in the sky, the strength of the tides, all are part of a continuum, shaped by processes that began long before complex life existed. During the age of Columbia, the difference in day length and lunar distance would not have seemed extraordinary to any living organism, because it was simply the normal state of the world. Only from our modern perspective does it appear unusual, a reminder that the Earth we know today is not a permanent or unchanging system. There is something calming in imagining those ancient nights. The moon rising over a quiet shoreline, waves moving in steady rhythms, the sky filled with stars, and no sound but wind and water. The same gravitational forces that move the oceans today were at work then, guiding the tides, shaping coastlines, and slowly altering the spin of the planet. Far beneath the quiet landscapes and shallow seas of Colombia, the most powerful forces shaping that world were at work, unseen but relentless. Mountains rose, continents shifted, and oceans opened or closed, all because of a deep engine operating thousands of kilometers below the surface. It moved slowly, far too slowly to notice within a lifetime, yet over millions of years it reshaped the entire planet. To understand this engine, it helps to imagine the Earth not as a solid, motionless sphere, but as a layered world. At the centre lies the core, intensely hot and dense. Surrounding it is the mantle, a vast region of rock that is solid in structure, but capable of flowing very slowly under immense heat and pressure. Above the mantle sits the crust, thin by comparison, broken into large pieces we call tectonic plates. These plates are not fixed. They drift, carried by convection currents in the mantle below. Hot material rises, cools, and sinks again, setting up slow circulations that move the plates above like rafts on a sluggish, thick fluid. During the time of Columbia, this deep engine may have been running somewhat faster than it does today. The Earth was younger then, and more heat remained trapped in its interior from the planet's formation and from the decay of radioactive elements. Higher internal heat can drive more vigorous convection, which in turn can lead to more active tectonics and volcanism. The assembly of Colombia itself was a result of these processes. Continental fragments moved gradually toward one another, colliding and welding together. Where plates converged, enormous forces compressed the crust, folding and thickening it to form mountain belts. These mountains were not necessarily identical to modern ranges like the Andes or Himalayas, but the fundamental processes that created them were the same. When two continental masses collide, neither easily sinks beneath the other, because continental crust is relatively light compared to the denser oceanic crust. Instead, the rocks crumple, thrust upward, and form thickened roots that extend deep into the mantle. Over time, erosion wears down the peaks, carrying sediments into nearby basins, but the roots of these mountains remain buried far below. In some regions of Colombia, these collision zones may have stretched for thousands of kilometers, forming broad belts of deformed and metamorphosed rock. Today, geologists can still recognize fragments of these belts, preserved in ancient terrains scattered across different continents. But not all plate boundaries were zones of collision. In other places, the crust was pulling apart. Heat rising from the mantle can weaken the crust, causing it to stretch and fracture. These rift zones form long valleys where the land gradually subsides. Over time, if rifting continues, the valley may fill with water and eventually widen into a new ocean basin. Such processes were already occurring during the time of Columbia, even while the supercontinent as a whole remained largely intact. Continents are never perfectly stable. They're always being reshaped by forces acting along their margins, and sometimes deep within their interiors. Volcanoes were one of the most visible expressions of these forces. Along subduction zones, where one plate sinks beneath another, melting occurs in the mantle above the descending slab. This molten material rises through the crust, feeding chains of volcanoes that can extend for great distances. Eruptions in such regions might have varied from quiet lava flows to explosive events that sent ash high into the atmosphere. Over thousands or millions of years, repeated eruptions built up layers of volcanic rock, forming mountains and plateaus. Elsewhere, volcanic activity occurred along rift zones, where magma rose through fractures in the crust. Lava could spread across broad areas, forming vast fields of basalt. These lava flows cooled into dark, dense rock that, over time, cracked and weathered, contributing to the landscape of the continent. Some of the most dramatic volcanic events may have been large igneous provinces, episodes when enormous volumes of magma erupted over relatively short geological timescales. These events could cover hundreds of thousands of square kilometers with lava, altering the atmosphere and climate by releasing gases such as carbon dioxide and sulfur compounds. The effects of such eruptions were not limited to the immediate region. Volcanic gases could spread through the atmosphere, influencing climate by trapping heat or reflecting sunlight, depending on their composition and the duration of the eruptions. Beneath the oceans, volcanic activity was equally important. Mid-ocean ridges, long chains of underwater volcanoes, produced new oceanic crust as magma rose and solidified. This newly formed crust gradually moved away from the ridge, carried by the motion of tectonic plates. Hydrothermal vents along these ridges released mineral-rich fluids into the surrounding water, creating localized environments where specialized microbial communities thrived. These vents were part of a broader cycle in which seawater circulated through the oceanic crust, interacting with hot rock and altering the chemistry of both water and minerals. The movement of tectonic plates also drove earthquakes, though in a world without buildings or cities, their effects would have been limited to landslides, ground rupture, and changes in the landscape. Over time, repeated seismic activity helped shape fault systems and influence drainage patterns, contributing to the long-term evolution of the terrain. Another important aspect of tectonics during the Age of Columbia was the growth of continental crust. When subduction occurs, some of the material rising from the mantle solidifies to form new granitic rocks, adding to the mass of continents. This process, repeated over hundreds of millions of years, gradually increased the size and stability of continental land masses. The cratons that formed the core of Colombia were the result of this long history of crustal growth. They represented regions where the crust had thickened and stabilized, resisting deformation even as surrounding areas continued to change. Heat from the mantle also influenced the elevation of the land. Regions where hot material rose closer to the surface could become uplifted, forming broad plateaus. Over time, as the mantle cooled or shifted, these regions might subside again, allowing seas to flood low-lying areas. This interplay between uplift and subsidence created a dynamic landscape, with coastlines advancing and retreating over geological time. Sediments deposited in shallow seas recorded these changes, forming layers that geologists can study today to reconstruct ancient environments. The deep engine of the planet was not only shaping the land but also influencing the atmosphere and oceans. Volcanic gases contributed to the composition of the air, affecting climate. The movement of continents altered ocean circulation, which in turn influenced temperature and weather patterns. All of these processes were interconnected, part of a complex system in which changes in one part of the planet could ripple outward to affect others. It is remarkable to consider how slowly these changes occurred. A continent might move only a few centimeters per year, about as fast as fingernails grow. Yet over 10 million years, that movement amounts to hundreds of kilometers. Over 100 million years, entire oceans can open or close, and continents can assemble or break apart. If you had stood on the land during the time of Columbia, you would not have felt the plates moving beneath your feet. The ground would have seemed solid and permanent. Only over immense spans of time would the effects become visible. Mountains rising, coastlines shifting, volcanoes building new land. This slow pace is one of the defining features of geology. The most powerful forces on Earth often act so gradually that they are invisible on human timescales, and yet, given enough time, they reshape the entire planet. As the deep engine continued to operate, eroding mountains supplied sediments to rivers, rivers carried those sediments to the sea, and weathering slowly altered the surface of the land. The sculpting of continents by wind, water, and chemical processes was just as important as the tectonic forces that built them. After mountains rise and volcanoes build new land, another set of forces begins its work almost immediately. These forces are quieter, less dramatic, and often overlooked, yet over long stretches of time they shape the continents just as profoundly as tectonics does. Rain falls, rivers flow, rocks break down, and grains of sediment begin journeys that may last hundreds or thousands of kilometers before coming to rest. During the time of Colombia, these processes were already well established, slowly sculpting the surface of the supercontinent in ways that would determine the landscapes of that ancient world. To begin with, weathering was constantly at work on exposed rock. Weathering is the process by which rocks are broken down at the surface through physical, chemical, and sometimes biological means. In the age of Colombia, biological weathering was limited compared to today, since there were no plants with roots to split rocks or organisms burrowing through soil in large numbers. Even so, physical and chemical weathering alone were powerful enough to reshape entire mountain ranges over millions of years. Physical weathering occurred when temperature changes caused rocks to expand and contract. During the day, sunlight warmed exposed surfaces, causing slight expansion. At night, cooling led to contraction. Repeated over countless cycles, these small changes created stresses that eventually caused cracks to form. Water seeping into those cracks could freeze in colder regions, expanding as it turned to ice and widening the fractures further. Over time, blocks of rock broke loose and fell, gradually reducing steep slopes to gentler forms. Wind also played a role, especially in dry regions where loose sediments were abundant. Fine particles lifted into the air could sandblast exposed rock, wearing it down grain by grain. Over long periods, this abrasion smoothed surfaces and contributed to the formation of sand and dust that could be carried far from their source. Chemical weathering was equally important, particularly in regions where rainfall was frequent. Rainwater absorbs small amounts of carbon dioxide from the atmosphere, forming a weak acid that reacts with minerals in rocks. These reactions slowly dissolve certain components, weakening the rock and producing new minerals such as clays. The dissolved material was carried away in solution, eventually reaching rivers and oceans. During the time of Colombia, chemical weathering played a significant role in regulating the atmosphere. As carbon dioxide dissolved in rainwater and reacted with rocks, it was gradually removed from the air and locked into minerals. Over geological timescales, this process helped balance the carbon dioxide released by volcanoes, contributing to the long-term stability of the planet's climate. Once rock was broken down into smaller fragments or dissolved into water, rivers became the main agents of transport. Rivers formed wherever rainfall or melting ice collected and began to flow downhill under the influence of gravity. Even without vegetation, drainage networks developed naturally, channels deepening as water followed the easiest path across the land. Rivers during the time of Colombia may have looked somewhat different from modern rivers, especially in their banks and floodplains. Without plant roots to stabilize soil, riverbanks were more prone to erosion, and channels may have shifted frequently, carving new paths across plains. Floods could spread sediments over wide areas, creating broad alluvial plains that slowly built up layer by layer. The water in these rivers likely carried high loads of sediment, especially during heavy rains. Suspended particles turned the water cloudy, sometimes giving it a reddish or brownish colour depending on the minerals present. As the current slowed, sediments settled out, forming sandbars, deltas and layers of mud that would eventually harden into rock. Over time, rivers carved valleys into the landscape. The process was gradual, almost imperceptible in the short term, but over millions of years entire canyon systems could form. The depth and shape of these valleys depended on factors such as the hardness of the rock, the slope of the land, and the volume of water flowing through the system. In mountainous regions, rivers often flowed swiftly, carrying coarse gravel and boulders. In lower, flatter regions, they slowed, depositing finer sediments such as sand and clay. These sediments accumulated in basins, forming thick sequences that preserved records of ancient climates and environments. Lakes also formed in some regions, particularly in low-lying basins created by tectonic activity or erosion. These lakes acted as temporary traps for sediment, allowing fine particles to settle in thin, even layers. Over time, these layers built up, preserving delicate structures such as ripple marks or traces of microbial activity. Another important aspect of weathering and erosion during this era was the absence of thick soils. Modern soils contain large amounts of organic material derived from plants and microorganisms. In the Age of Columbia, soils were thinner and more mineral-rich, formed primarily through the breakdown of rock rather than through the accumulation of decayed vegetation. This difference influenced how water moved across the land. Thin soils allowed water to run off more quickly, increasing erosion in some areas. Sediments were transported efficiently to rivers and then to the sea, where they accumulated along continental margins. At the coast, rivers met the ocean, depositing sediments in deltas and estuaries. These environments were dynamic, shaped by the interaction of river currents, waves, and tides. Channels shifted, sandbars formed and disappeared, and layers of sediment built up in patterns that reflected changing conditions. In shallow marine environments, sediments carried by rivers provided nutrients that supported microbial communities. Fine particles settled gently to the sea floor, sometimes forming laminated deposits that recorded seasonal or annual cycles. The quiet sculpting of continents was not limited to water and wind. Gravity itself played a constant role. Landslides and rockfalls occurred where slopes became unstable, especially after heavy rains or earthquakes. These sudden movements transported large volumes of material downslope, contributing to the gradual lowering of mountains and the filling of valleys. Over immense spans of time, the combined effects of weathering, erosion, and sedimentation reshaped entire regions. Mountain ranges worn down, basins filled, and landscapes that had once been rugged became smoother and more subdued. The sediments carried away from highlands eventually became part of new rocks, buried and compressed, sometimes uplifted again in future tectonic events. This cycle, uplift, erosion, deposition, burial, and uplift again, is one of the great rhythms of Earth's surface. It operated during the time of Columbia just as it does today, though the details differed because of the absence of vegetation and the different composition of the atmosphere. Rainfall patterns influence where erosion was most intense. Regions receiving frequent rains experienced faster weathering and more active river systems, while drier areas were shaped more by wind and occasional floods. The distribution of mountains and plains affected these patterns, creating areas of heavy runoff and others where water was scarce. Chemical weathering also influenced the chemistry of rivers and oceans. Dissolved minerals carried by rivers contributed to the composition of seawater, affecting processes such as the formation of carbonate rocks and the availability of nutrients for marine life. It is easy to overlook how important rivers are in shaping the planet, because their work is usually quiet and gradual. A river does not carve a valley in a single season, or build a delta in a single year. It does so grain by grain, layer by layer, over spans of time so long that entire landscapes can change without any dramatic events. If you could stand on the bank of a river in the time of Columbia, you might see water flowing steadily over a rocky bed, carrying sand and silt toward the sea. The sound of the current would be familiar, a gentle, continuous motion. The surrounding land would be bare compared to modern landscapes, but the processes shaping it would be the same ones still at work today. In the distance, mountains slowly wore down, their sediments beginning long journeys through river systems. Along the coast, waves and tides reshaped shorelines, redistributing material carried from inland. Beneath the surface, tectonic forces continued to raise new land even as erosion wore the old away. This balance between construction and destruction, between uplift and erosion, defined the landscapes of Colombia. Nothing remained unchanged forever, yet nothing changed quickly. The continents were always in motion, always being reshaped, but on timescales measured in millions of years rather than days or seasons. For hundreds of millions of years, Colombia remained largely intact, a vast landmass stitched together from older fragments of crust. Mountains rose and eroded, rivers carried sediments to the sea, and the atmosphere and oceans continued their slow transformations. From the perspective of a single human lifetime, if one could have existed then, the continent would have seemed permanent, immovable, and unchanging. Yet deep beneath the surface, the forces that had assembled Colombia were still at work, and over time those same forces began to pull it apart. The breakup of a supercontinent does not begin with a dramatic crack running across the land. It starts quietly, often deep below the crust, where heat accumulates in the mantle. When a large continent sits over the mantle for long periods, it can act like an insulating blanket trapping heat beneath it. Over millions of years, this trapped heat can weaken the lower crust and upper mantle, making the lithosphere more prone to stretching and fracturing. As the rock beneath Colombia warmed and softened, stresses began to build. These stresses were not sudden or violent. They developed gradually, as convection currents in the mantle shifted, and as the thick continental crust responded to forces acting from below and at its edges. Eventually, in certain regions, the crust began to stretch. Stretching does not immediately create oceans or even wide valleys. At first, it produces fractures, faults, and zones where the land slowly subsides. These early rift zones might appear as long, shallow depressions, bordered by faults where blocks of crust moved relative to one another. Volcanic activity often accompanied this stretching, as magma rose through newly formed cracks, sometimes reaching the surface as lava flows. Imagine a broad region of land where the ground is gradually pulling apart. Over thousands or millions of years, small earthquakes occur as faults adjust. Volcanic eruptions release lava and gases. Lakes may form in the low-lying areas created by subsidence, gradually filling with sediments washed in from surrounding highlands. These early stages of rifting can persist for very long periods, without leading to complete separation of the continent. Some rifts fail, becoming geological scars that record an attempt at breakup that never fully succeeded. Others continue to widen, eventually allowing seawater to enter and forming narrow seas that may later expand into full ocean basins. Evidence suggests that Colombia began to fragment sometime around 1.6 to 1.5 billion years ago, though the exact timing and sequence of events vary depending on which regions are examined. The breakup was not a single event, but a prolonged process, with different parts of the supercontinent separating at different times. As rifting progressed, the crust thinned in affected regions. Thinner crust is more likely to fracture and allow magma to rise, which in turn weakens the crust further. This feedback can accelerate the process of separation. Eventually, if rifting continues long enough, new oceanic crust begins to form between the separating land masses. When this happens, the continent is no longer a single continuous landmass. A new ocean basin begins to open, gradually widening as tectonic plates move apart. The edges of the continents become passive margins, where thick layers of sediment accumulate over time. During the breakup of Colombia, similar processes were likely occurring in multiple regions. Fragments of crust that had once been joined began drifting away from one another, carried by the motion of tectonic plates. Mountain belts that had formed during the continent's assembly were slowly eroded, their sediments deposited in newly forming basins. Volcanism played a significant role in this transition. Large-scale volcanic events, sometimes referred to as large igneous provinces, may have accompanied the breakup, releasing vast quantities of lava and volcanic gases. These eruptions could cover extensive areas, creating thick sequences of basalt and altering the atmosphere and climate. The gases released during such eruptions included carbon dioxide, sulfur compounds, and water vapour. Over long periods, increased carbon dioxide could contribute to warming, while sulfur aerosols might produce short-term cooling by reflecting sunlight. The balance between these effects depended on the scale and duration of the eruptions. As continents separated, ocean circulation patterns changed as well. New seaways allowed water to flow between regions that had previously been isolated. Currents shifted, redistributing heat and nutrients, influencing climate and marine ecosystems. The breakup of a supercontinent is therefore not just a geological event, but a transformation that affects the entire Earth system: land, sea, atmosphere, and life. On the surface, the landscapes of Colombia during this time would have shown signs of change. Rift valleys widened slowly, sometimes forming chains of lakes or shallow seas. Volcanic fields spread across certain regions. Fault scarps rose where blocks of crust moved, creating steppe-like landscapes. Rivers adjusted their courses in response to these changes, flowing into new basins or toward newly formed coastlines. Sediments accumulated in rift valleys, recording the early stages of continental separation in layers of sandstone, shale, and volcanic ash. Over millions of years, these sediments were buried, compressed, and preserved, providing evidence that geologists can study today to reconstruct the history of the breakup. One of the challenges in understanding Colombia's fragmentation is that much of the oceanic crust formed during this time has long since been recycled into the mantle. Oceanic crust rarely survives for more than a few 100 million years before being subducted, so direct evidence of the earliest ocean basins that formed during Colombia's breakup is scarce. Instead, scientists rely on clues preserved in continental rocks, rift-related volcanic sequences, sedimentary basins, and paleomagnetic data that record the movement of continental fragments over time. By comparing these records from different parts of the world, researchers can piece together a picture of how Colombia gradually broke apart, giving rise to smaller continents and eventually setting the stage for the formation of the next supercontinent, Rodinia. It's important to remember that this process unfolded over immense spans of time. From the first signs of rifting to the complete separation of major continental blocks may have taken tens or even hundreds of millions of years. There was no single moment when Colombia ceased to exist. Instead, it slowly transformed, its unity fading as its fragments drifted farther apart. If you could have watched this transformation in real time, the changes would have been almost imperceptible. Coastlines shifting by a few meters in a lifetime, valleys deepening slightly over centuries, volcanic fields growing slowly with each eruption. Only by stepping back and looking across millions of years would the full scale of the breakup become clear. There is something quietly humbling in that perspective. The continents we live on today are temporary arrangements, just as Colombia was. They will continue to move, collide, and separate long after our own time has passed. During the final stages of Colombia's fragmentation, new ocean basins widened, isolating continental fragments that would follow their own geological paths. Mountain belts formed during earlier collisions were worn down, and sediments filled basins along the edges of the drifting continents. The climate, the oceans, and the atmosphere all responded to these changes, adjusting gradually to new patterns of circulation and geography. As the fragments of Colombia continued drifting apart, the surface of the planet entered another long transitional period, one that unfolded so slowly that, If you could have watched it from a fixed point on the ground, you might have seen almost nothing change from one lifetime to the next. Mountains still eroded, rivers still carried sediment, and shallow seas still rose and fell along the margins of land. Yet beneath that calm appearance, the rearrangement of continents was underway, guiding the planet toward a new configuration that would eventually become known as Rodinia. To picture this interval, it helps to let go of the idea that continents move with any urgency. Even today, tectonic plates travel at rates comparable to the growth of fingernails. Over a year, the motion is only a few centimetres. Over a century, a few metres. Only when time stretches into millions of years does the movement become unmistakable. Oceans open, mountain belts appear, continents that were once neighbours drift to opposite sides of the globe. After Colombia began to fragment, its pieces did not scatter randomly. Their motion was guided by convection currents in the mantle, the slow circulation of hot and cooler rock far below the crust. These currents are not chaotic in the way storms in the atmosphere are chaotic. They are steady, persistent flows that evolve gradually, influencing the direction and speed of tectonic plates over immense spans of time. As rifting progressed, new oceanic crust formed in widening gaps between continental fragments. Seawater filled the low-lying regions, creating narrow seas that slowly broadened. Along the edges of these new basins, sediments accumulated in thick layers, washed in by rivers and shaped by tides and waves. These sediments preserved records of changing environments, evidence that geologists would one day use to reconstruct the history of these ancient separations. During this time, the climate and oceans continued to respond to shifting geography. The positions of continents influence ocean currents, and currents in turn influence temperature and weather patterns. When land blocks move, they alter the pathways through which heat is transported around the planet. Over millions of years, these changes can reshape regional climates, sometimes subtly, sometimes more dramatically. The breakup of Colombia also influenced volcanic activity. Rift zones and plate boundaries remained active, releasing magma and gases. In some regions, large volcanic provinces may have formed, covering extensive areas with basaltic lava. These eruptions were not necessarily continuous or catastrophic in a human sense, but over thousands or millions of years they added layer upon layer of volcanic rock to the crust. At the same time, other regions experienced quieter geological histories, where erosion dominated and landscapes slowly wore down. The contrast between tectonically active zones and stable interiors created a mosaic of environments, some shaped by fire and uplift, others by wind, water, and time. While the continents were separating in some areas, they were also beginning to converge in others. This is one of the most important features of the supercontinent cycle. Breakup and assembly are not entirely separate phases but overlapping processes. As some ocean basins widen, others begin to close. Plates that once moved apart eventually change direction, guided by evolving patterns of mantle convection and the forces acting at plate boundaries. Over tens of millions of years, fragments of Colombia drifted across the surface of the Earth, gradually approaching new neighbours. When continents collide, the oceanic crust between them is subducted, sinking back into the mantle. Eventually, the continents themselves meet, and new mountain belts rise along the collision zones. These collisions were the first steps toward the assembly of Rodinia, the supercontinent that would follow Colombia. The process did not happen all at once or in a single place. It occurred in stages, with different continental blocks joining at different times, forming a growing network of connections that would eventually produce a vast landmass. The formation of mountain belts during these collisions left behind geological signatures that remain visible today. Rocks that were once buried deep in the crust were brought to the surface through uplift and erosion, revealing evidence of intense pressure and heat. By dating these rocks and studying their structures, geologists can trace the timing and sequence of ancient collisions, piecing together the story of how continents came together again. One of the remarkable aspects of this long interval between Colombia and Rodinia is that life continued to evolve quietly in the background. Microbial ecosystems remained dominant, but the gradual rise of oxygen and the diversification of early eukaryotes were setting the stage for future biological changes. These developments were slow, unfolding over hundreds of millions of years, but they were shaping the planet in ways that would eventually allow more complex life to emerge. The oceans too were changing as continental arrangements shifted. The opening and closing of seaways influenced circulation patterns, affecting the distribution of nutrients and oxygen. In some regions, shallow inland seas formed, creating environments where sediments accumulated and microbial communities flourished. In others, deeper basins developed, where fine particles settled slowly through dark, quiet water. Sea level itself rose and fell over long timescales, influenced by tectonic activity, climate, and the volume of ocean basins. When seafloor spreading rates were high, ocean ridges occupied more space, displacing seawater and raising global sea levels. When spreading slowed or ocean basins deepened, sea levels fell, exposing continental shelves and altering coastlines. These changes were gradual but far-reaching. Shorelines advanced and retreated, river systems adjusted to new gradients, and ecosystems adapted to shifting conditions. Even in a world dominated by microorganisms, environmental changes influenced the distribution and abundance of life. Another factor shaping this transitional era was the continuing interaction between the atmosphere and the land. Weathering of rocks removed carbon dioxide from the air, helping regulate climate over long periods. Volcanic emissions added gases back into the atmosphere, maintaining a balance that prevented extreme swings in temperature for most of this time. This slow increase in oxygen levels continued as well, though the process was uneven. Some intervals saw rising concentrations, while others experienced plateaus or slight declines. The balance between oxygen production and consumption was influenced by many factors, including volcanic activity, the burial of organic carbon, and the chemistry of the oceans. If you imagine standing on a coastline during this era, the scene would still feel quiet and stark compared to the modern world. The land would be largely barren, the sea dominated by microscopic life, the air carrying only the sounds of wind and water. Yet the position of the stars, the phases of the moon, and the rhythm of tides would feel familiar. Reminders that the fundamental motions of the Earth-Moon system continued unchanged. Far inland, rivers would flow across wide plains, carrying sediments toward the sea. In mountainous regions, erosion would slowly reduce peaks that had formed during earlier collisions. In volcanic regions, new rock would spread across the surface, later to be weathered and eroded in its turn. Everything was part of a cycle, continents assembling and breaking, mountains rising and wearing down, oceans opening and closing. The time between Colombia and Rodinia was not an empty interval, but a period of continuous change, a bridge between two great configurations of the planet's surface. As continental fragments approached one another, the pace of mountain building increased in certain regions. Subduction zones consumed oceanic crust, drawing continents closer together. Island arcs formed where volcanic chains rose above the sea, eventually colliding with larger landmasses and adding new material to the continents. These processes gradually reduced the distances between major continental blocks. Over tens of millions of years, collisions welded them together, forming larger and larger assemblies of crust. The outlines of Rodinia began to take shape, though it would be a long time before the supercontinent reached its full extent. The assembly of Rodinia, like the assembly of Colombia before it, was not a single event but a prolonged sequence of collisions and adjustments. Continents rotated, shifted, and settled into new positions, guided by forces deep within the mantle. The landscape during this time would have been dynamic in geological terms, though still calm from the perspective of daily experience. Earthquakes shook the ground in tectonically active regions. Volcanoes erupted intermittently. Rivers continued their steady work and the climate fluctuated within ranges that allowed oceans to remain liquid and life to persist. It is worth pausing to reflect on how immense these timescales are. The interval between the breakup of Colombia and the full assembly of Rodinia spans hundreds of millions of years, far longer than the time separating the age of dinosaurs from the present day. Entire mountain ranges rose and eroded within that span. Oceans opened and closed. Atmospheric composition shifted, and life continued its slow evolution. And yet, all of these changes were part of a single continuous story, the ongoing evolution of a planet shaped by internal heat, solar energy, and the activities of living organisms. Eventually, Rodinia would become the dominant supercontinent, reshaping ocean circulation, climate, and the distribution of a life once again. But that stage lay ahead, still forming, still incomplete during the later phases of Colombia's fragmentation. As we follow this long progression, it becomes clear that no arrangement of continents is permanent. Each configuration is temporary, lasting hundreds of millions of years at most before the cycle begins again. The continents we know today are only the latest chapter in a story that has repeated many times and will continue long into the future. Looking back at the long story of Colombia, one of the most important things it offers us is not only a picture of a distant world, but a deeper understanding of how planets like Earth behave over immense spans of time. Colombia is not simply an isolated episode in geological history. It is part of a repeating pattern, a rhythm of assembly and breakup that has shaped the surface of our planet again and again. By studying that pattern, scientists have begun to understand something profound about the way continents move, how the interior of Earth releases heat, and why supercontinents form at all. To appreciate what Colombia teaches us, it helps to step back and think about the continents not as fixed pieces of land, but as parts of a system in constant motion. Today, the continents seem stable because their movement is so slow that it is impossible to notice without precise instruments. But over tens or hundreds of millions of years, continents travel across the globe, oceans open and close, and entirely new configurations of land emerge. Colombia was one of the earliest large supercontinents that scientists can reconstruct with reasonable confidence. Before it, there may have been others, but the evidence becomes more fragmentary the farther back in time we go. After Colombia came Rodinia, and much later, Pangea. Each of these supercontinents formed through the gradual collision of smaller landmasses and later broke apart, beginning the cycle again. What becomes clear from this pattern is that supercontinents are not rare accidents. They are a natural consequence of plate tectonics operating over long time scales. The motion of tectonic plates is driven by heat from Earth's interior, and that heat must eventually escape. One of the ways the planet releases heat is through the creation and destruction of oceanic crust, the spreading of sea floors, and the subduction of plates back into the mantle. When continents are scattered, ocean basins can be wide, and subduction zones may be distributed around the edges of multiple plates. Over time, however, the motion of plates tends to draw continents together. Oceanic crust between them is consumed, and eventually the continents collide, forming a supercontinent. But the story does not end there. A large supercontinent acts like an insulating blanket over the mantle. Heat builds beneath it, weakening the crust and eventually leading to rifting and breakup. New ocean basins form, the continents separate, and the cycle begins again. This sequence, assembly, insulation, breakup, and dispersal, appears to be a fundamental feature of Earth's long-term evolution. Colombia provides one of the earliest clear examples of this cycle in action. Another lesson Colombia offers concerns the timescales involved. It is difficult for the human mind to grasp durations of hundreds of millions of years. Civilizations rise and fall in a few thousand years. Even the entire history of human beings as a species covers only a small fraction of a million years. Yet supercontinents exist, change, and disappear over periods so vast that entire mountain ranges can rise and erode away while the process unfolds. Understanding this helps put the present into perspective. The continents we know today, Africa, Eurasia, the Americas, Antarctica, Australia, are not permanent features. They are temporary arrangements, snapshots in a long sequence of shifting geography. Tens or hundreds of millions of years from now, they will look very different. Colombia also teaches us about the stability and resilience of continental crust. The cratons that formed its core were already ancient at the time, and many of them still exist today. These stable regions of crust have survived multiple cycles of collision and breakup, preserving rocks that record events billions of years old. By studying these cratons, scientists can trace the history of continents far into the past. The rocks act as archives, storing evidence of volcanic activity, sedimentation, metamorphism, and erosion. Each layer, each mineral, carries information about the conditions under which it formed. This ability of continents to preserve their history is one of the reasons we can reconstruct worlds as ancient as Colombia. Oceanic crust is continually recycled into the mantle, erasing most of its record, but continental crust endures, allowing fragments of ancient landscapes to survive into the present. Another insight gained from Colombia concerns the interaction between geology and climate. The arrangement of continents influences ocean currents, atmospheric circulation, and the distribution of rainfall. When a supercontinent forms, it alters these systems on a global scale. Large continental interiors tend to be dry, because moisture from the oceans must travel long distances to reach them. Mountain ranges formed during continental collisions can block winds and create rain shadows. Ocean currents are redirected by the presence of large land masses, changing the way heat is transported around the planet. These effects were present during the time of Colombia, just as they were during the time of Pangea. By comparing different supercontinents, scientists can see patterns in how climate responds to changes in geography. Colombia also provides clues about the evolution of the atmosphere and oceans. During its existence, oxygen levels were rising, microbial life was transforming the chemistry of seawater, and the planet was moving gradually toward conditions that would eventually support more complex organisms. The connection between geology and biology is another important lesson. Tectonic activity influences the distribution of nutrients, the formation of shallow seas, and the cycling of elements such as carbon and phosphorus. These factors, in turn, affect the evolution of life. In this way, the formation and breakup of supercontinents are not merely geological events, they are part of a larger system that shapes the entire biosphere. It is also worth considering how scientists have come to understand all of this. The reconstruction of Colombia required combining evidence from many different fields: geology, geochemistry, paleomagnetism, geochronology, and more. No single method could have revealed the full picture. Rocks had to be dated using radioactive decay in minerals such as zircon. Magnetic signatures preserved in ancient lava flows had to be measured and interpreted. Mountain belts on different continents had to be compared and correlated. Each piece of evidence was like a fragment of a puzzle, and only by assembling many fragments could scientists begin to see the outline of the ancient supercontinent. This process continues today. New discoveries refine our understanding, sometimes confirming earlier models, sometimes suggesting revisions. The picture of Colombia is not fixed or final, it is an evolving reconstruction, becoming clearer as new data emerge. Another important lesson from Colombia is that the surface of Earth is always in transition, even when it appears stable. Mountains are rising and eroding at the same time. Sediments are being deposited even as other rocks are being worn away. Continents are moving, even if the motion is too slow to perceive directly. This continuous change is one of the defining characteristics of our planet. Unlike Mars or the Moon, where tectonic activity has largely ceased, Earth remains geologically active. Its interior heat drives processes that reshape the surface over and over again. The existence of supercontinents is one expression of this activity. They are milestones in a long journey, markers of stages in the evolution of the planet's crust. There is also something quietly humbling in realizing how long these cycles have been operating. Colombia formed and broke apart long before animals existed. Rodinia came and went before complex ecosystems appeared on land. Pangea assembled and fragmented while dinosaurs ruled the Earth. Each supercontinent witnessed a different world, different climates, different forms of life. Yet the underlying processes remain the same: plates moving, oceans opening, mountains rising, and erosion wearing them down again. Thinking about this can change the way we see the present. The landscapes around us, the mountains, the rivers, the coastlines, are not permanent. They are part of a story still unfolding, shaped by forces that began long before humans appeared, and that will continue long after we are gone. Colombia also reminds us that much of Earth's history is hidden. The farther back we look, the fewer rocks remain intact, and the more difficult it becomes to reconstruct past environments. Entire ocean basins have vanished without leaving direct traces. Mountain ranges have been worn down to their roots. Sediments have been buried, metamorphosed, or subducted. And yet enough evidence survives to tell a story that grows richer as techniques improve and new discoveries are made. Another perspective Colombia offers is about the pace of change. In human experience, change often feels rapid. Technology advances, cities grow, climates shift over decades or centuries. But geological change operates on timescales so vast that even dramatic events, volcanic eruptions, earthquakes, asteroid impacts, become small details in a much longer narrative. The breakup of a supercontinent, which might seem like a sudden event when described in a few sentences, actually unfolds over tens of millions of years. Entire oceans open gradually, widening a few centimeters each year. Continents drift apart slowly, their separation measurable only through careful observation over long periods. This sense of deep time can be difficult to grasp, but it is essential for understanding the history of Earth. Perhaps one of the most profound lessons Colombia teaches is that our planet is not static but dynamic, not finished but continually evolving. The continents, the oceans, the atmosphere, and life itself are all part of an interconnected system, responding to changes and influencing one another. The world we know today is only one stage in that long evolution. Just as Colombia once existed and then disappeared, the present arrangement of continents will one day give way to another. New supercontinents will form in the distant future, shaped by the same forces that assembled Colombia so long ago. There is a quiet continuity in that thought. The processes shaping Earth today are the same ones that shaped it billions of years ago. The rivers still flow, the winds still move, the mantle still convects, and the plates still drift. And as we continue to reflect on what Colombia teaches us, another question begins to emerge, one that connects the distant past to the present more directly. Why does any of this matter to us now? What does the story of an ancient supercontinent, long vanished and almost forgotten, tell us about the world we live in today and the future that lies ahead? It may seem at first that a world as distant as Colombia belongs entirely to the past, disconnected from the present in any practical sense. After all, more than 1 billion years separate that ancient supercontinent from the landscapes we know today. No mountains from that time remain in their original form, no oceans from that era still exist, and no living organism on Earth today remembers it in any direct way. Yet the deeper scientists look, the clearer it becomes that these ancient worlds still matter, not only because they tell us where the planet has been, but because they help explain where it is now and where it may be going. One of the most direct ways the Age of Columbia continues to influence the present is through the continents themselves. The land we live on today is built upon foundations that formed long before complex life appeared. Many of the cratons that made up Colombia still exist as the stable cores of modern continents. These regions preserve rocks that record ancient events, volcanic eruptions, mountain building, sedimentation, and the slow changes of the atmosphere and oceans. When geologists study these rocks, they're not only reconstructing distant landscapes, they're also learning about the processes that continue to shape Earth today. The same tectonic forces that assemble Colombia are still moving the continents. The same cycles of erosion and sedimentation are still reshaping the land. The same interactions between atmosphere, oceans, and life continue to influence climate. Understanding these processes in the deep past gives scientists a longer timeline, a broader perspective that helps them recognize patterns that would otherwise be invisible. A few decades of climate observations can reveal trends, but billions of years of geological history reveal the full range of conditions the planet can experience. For example, studying ancient atmospheres helps scientists understand how carbon dioxide, oxygen, and other gases influence temperature and climate. During the time of Columbia, greenhouse gases helped keep the planet warm despite a dimmer sun. Later, changes in atmospheric composition contributed to periods of glaciation. These ancient examples provide valuable context for understanding how the climate system responds to changes in greenhouse gas concentrations. Another reason these ancient worlds matter is that they show how life and the planet influence one another. Microorganisms during the time of Columbia gradually increased oxygen levels in the atmosphere, transforming the chemistry of the oceans and paving the way for more complex life. This long process demonstrates that life is not merely a passenger on Earth, but an active participant in shaping its environment. Today, the influence of life on the planet continues, though in different ways. Forests, algae, and microorganisms still affect atmospheric composition, nutrient cycles, and climate. Humans, too, have become a geological force, altering landscapes, changing the composition of the atmosphere, and influencing ecosystems on a global scale. By studying earlier transformations, scientists gain insight into how planetary systems respond to large-scale changes. There is also a practical dimension to understanding ancient geology. Many of the resources that support modern society originated in processes that took place hundreds of millions, or even billions of years ago. Iron deposits formed in ancient oceans, shaped by the interaction of oxygen and dissolved minerals, now provide the raw material for steel used in buildings, bridges, and machines. Certain mineral deposits formed during ancient volcanic or tectonic events are mined today for elements used in electronics, renewable energy technologies, and countless everyday objects. The distribution of these resources is closely tied to the geological history of continents. By studying the formation and breakup of supercontinents like Colombia, geologists can better understand where certain types of mineral deposits are likely to be found. Ancient worlds also matter because they remind us that Earth is not static. The continents have moved across the globe many times, oceans have opened and closed, climates have shifted, and life has changed in ways that would have been unimaginable at earlier stages. This perspective can change how we think about the present. It shows that change is not an exception in Earth's history, but the rule. At the same time, understanding past changes helps distinguish between natural variations and changes driven by new factors. Geological records reveal how climate responded to shifts in volcanic activity, continental positions, and atmospheric composition in the past. By comparing those patterns with modern observations, scientists can better understand the causes of current changes and the possible outcomes in the future. Another important lesson from studying ancient worlds is the scale of time itself. Human experience is measured in years or decades, but the processes that shape planets operate over millions or billions of years. Mountains rise and erode, continents assemble and break apart, oceans change their chemistry, and life evolves in slow, steady steps. Recognizing this scale can be both humbling and reassuring. It reminds us that the planet is resilient, capable of enduring enormous changes, Yet it also shows that some changes, once set in motion, can last far longer than any human institution or civilization. There is also something deeply meaningful in understanding that the Earth has a history far older than humanity. The landscapes around us are not merely backdrops to our lives. They are the result of countless events, collisions, eruptions, floods, and slow transformations stretching back billions of years. Every rock carries a story, every layer of sediment a memory of a vanished environment. Learning about worlds like Colombia helps us see the present in a different light. The mountains we see today are part of a long chain of mountain ranges that have risen and fallen through time. The oceans have changed their shapes many times. Even the air we breathe is the result of processes that began long before animals existed. In a quieter way, these ancient worlds also influence how we think about the future. The supercontinent cycle suggests that continents will continue to move, eventually forming new supercontinents tens or hundreds of millions of years from now. While such timescales are far beyond human planning, they remind us that the planet's story is still unfolding. Some scientists have even modelled possible future configurations of continents, predicting that the Atlantic Ocean may eventually close, that new mountain ranges may rise where oceans now lie, and that climates will change as geography shifts. These predictions are not precise in detail, but they are grounded in the same processes that shaped Colombia and later supercontinents. There is also a broader scientific importance in studying ancient worlds. Earth is the only planet we know where life has existed for billions of years. By understanding how Earth's environment has changed over time, scientists gain insights that may help in the search for life on other planets. If we discover a world with an atmosphere rich in oxygen, for example, it may suggest biological activity, just as it does on Earth. The history of oxygen on our own planet, including the slow changes during the time of Colombia, provides a model for how life can transform a planet's atmosphere. This knowledge guides astronomers as they study distant worlds, looking for signs of similar processes. Ancient geology also helps scientists understand how planets cool and evolve internally. The movement of tectonic plates, the formation of supercontinents, and the release of heat from the mantle are all part of a planet's long-term development. By studying these processes on Earth, researchers gain clues about why some planets remain geologically active while others become quiet and frozen. Mars, for example, shows evidence of ancient rivers and volcanoes, but no longer has active plate tectonics. Venus may have experienced different kinds of tectonic processes altogether. Earth's history, including the age of Columbia, offers a valuable point of comparison. There is another, more reflective reason these ancient worlds matter. They invite us to step outside the pace of everyday life and see the planet from a wider perspective. When we think about billions of years of history, about continents assembling and breaking apart, about life slowly transforming the atmosphere, the concerns of a single day or even a single year begin to feel smaller. This does not make those concerns unimportant, but it places them within a larger context. It reminds us that we are part of a much longer story, one that began long before us and will continue long after. Imagine standing on a quiet shoreline at night, listening to the waves and looking up at the stars. The same stars shone over the oceans of Colombia. The same moon raised tides along its coasts. The same planet turned beneath the sky, carrying continents across its surface in motions too slow to see. That continuity connects us to the distant past in a way that is both scientific and deeply human. We are inhabitants of a planet with a long memory, even if we are only beginning to learn how to read it. Understanding ancient worlds also encourages patience in the way we think about natural processes. Geological changes often occur gradually, but their cumulative effects can be enormous. A river flowing quietly today may carve a canyon over millions of years. A small increase in atmospheric oxygen can, over long periods, reshape ecosystems and enable entirely new forms of life. These examples remind us that small changes, given enough time, can lead to profound transformations. At the same time, studying ancient environments teaches us that Earth's systems are interconnected. Changes in one part of the system often ripple outward, affecting others. The breakup of a supercontinent alters ocean currents, which influence climate, which in turn affects erosion and sedimentation, which can influence the chemistry of the oceans and atmosphere. This interconnectedness is still present today. The atmosphere, oceans, land, and biosphere are linked in complex ways, responding to both natural and human influences. And so, when we look back at Colombia, we are not merely looking at a vanished landmass, we are looking at an earlier chapter in the story of a planet that continues to change. The lessons we learn from that chapter help us understand the present and prepare for the future. The continents beneath our feet were shaped by events that began long before humans existed. The air we breathe is the result of ancient biological processes. The minerals in the ground, the patterns of rivers, the distribution of mountains, all are part of a history that stretches back billions of years. Now, after travelling so far back through time, it helps to slow down for a moment and let the mind settle again in the present. We have wandered across landscapes that no longer exist, watched continents assemble and drift apart, imagined oceans filled only with microscopic life, and stood beneath skies where the air itself was still changing. The world of Colombia feels distant, almost unreal, and yet it was not a different planet. It was this one, the same Earth beneath your feet right now, simply at an earlier stage in its long and quiet story. If you think about it, the ground beneath you carries that history even now. Every continent is built from fragments of older worlds, layers upon layers of rock recording events that happened long before any human voice was ever heard. The hills, plains, and coastlines we see today are the latest arrangement, shaped by forces that have been at work for billions of years and are still moving, still reshaping the surface, even as we go about our daily lives. It is easy to forget this, because most of the time the planet feels steady and unchanging. Buildings stand for decades, cities for centuries, and even mountains seem permanent when measured against the span of a human life. But the deeper rhythm of Earth moves on a different scale, a slow, patient pace in which entire oceans can appear and vanish, in which continents drift across hemispheres, and in which climates shift so gradually that only rocks remember how different the world once was. Thinking about Colombia brings that deep rhythm into focus. A supercontinent formed, endured for hundreds of millions of years, and then slowly fragmented, giving way to new arrangements of land and sea. Long after it was gone, other supercontinents followed, and still others will come in the distant future. The cycle continues, steady and unhurried, guided by heat rising from the mantle and by the quiet motion of tectonic plates. There is something calming in that continuity. The same physical laws that shaped Colombia are shaping the world today. Gravity still pulls rivers toward the sea. Heat still rises from the planet's interior. Winds still move across the oceans, carrying moisture and shaping weather. The sun still rises each morning just as it did more than 1 billion years ago, shining on continents that looked completely different, but felt the same warmth. If you imagine standing on a shoreline now, perhaps hearing waves in the distance or remembering the sound of them, it is comforting to realize that waves have been breaking on rocky coasts for most of Earth's history. Long before animals walked on land, long before forests covered the continents, tides were rising and falling, guided by the moon, just as they do tonight. And the moon itself, slowly drifting farther away over immense spans of time, has watched all of this unfold. It shone over the oceans of Colombia, over the first microbial mats in shallow seas, over the slow rise of oxygen in the atmosphere. It shines now over cities and forests and fields, and it will continue to shine over landscapes that have yet to form. These connections between past and present can change the way we see the world around us. A rock on the ground is no longer just a rock. It is part of a story that stretches back beyond memory, a fragment of processes that shaped entire continents. A grain of sand on a beach may have been eroded from a mountain that rose and wore away long before the first animals appeared. Even the air we breathe carries that history. The oxygen filling your lungs is the result of ancient biological processes that began billions of years ago, when microorganisms in the oceans slowly transformed the atmosphere. Every breath connects us, in a quiet way, to that distant past. It is not necessary to think about these things all the time, of course. Life is full of immediate concerns, responsibilities, and moments that demand attention. But sometimes, especially in quiet hours, it can be comforting to step back and see the larger picture, to remember that the world is older and more enduring than any single moment of worry or stress. The Earth has been through immense changes, climates warmer and colder than today, continents gathered and scattered, life nearly extinguished and then flourishing again. Through all of this, the planet continued, reshaping itself, adapting, renewing. There is a quiet resilience in that history. Not the kind of resilience that means nothing ever changes, but the kind that means change itself is part of the system, part of the ongoing flow of energy and matter that keeps the planet alive and dynamic. As you settle into the present again, you might notice the small, steady rhythms around you, the sound of your own breathing, the faint movement of air in the room, perhaps distant sounds from outside, softened by distance and walls. These gentle, ordinary sensations are part of the same world that once held Colombia, the same planet that continues to move through space, orbiting the sun, turning slowly on its axis. Time, in this sense, becomes less like a straight line and more like a wide landscape, stretching far behind us and far ahead. We stand in one small place within it, aware of only a tiny fraction, yet connected to the whole. There is also something quietly reassuring in realizing how much of Earth's history unfolded without urgency. The breakup of a supercontinent took tens of millions of years. The rise of oxygen took hundreds of millions. Even the formation of mountain ranges, which can seem dramatic, occurred grain by grain, layer by layer, over spans of time almost beyond comprehension. This slow pace is a reminder that not everything important happens quickly. Some of the most profound changes are the ones that unfold so gradually they are almost invisible, noticeable only when viewed from far enough away. And perhaps that thought can be comforting as well. Just as landscapes change slowly, so does many aspects of life. Growth, understanding, healing, and learning often happen quietly, without sudden transformation, but with steady progress over time. Returning now to the present moment, you might imagine the planet as it is right now, a blue sphere turning silently in the darkness of space. Clouds drift across the oceans, winds move across continents. Somewhere, rivers flow through valleys, carrying sediments toward the sea, just as they have for billions of years. Far below the surface, the mantle continues its slow circulation, moving the tectonic plates by a few centimeters each year. The continents are still drifting, though the motion is too small to feel. In millions of years, the arrangement of land will be different again, but tonight, everything feels still and calm. If you look up at the night sky, or imagine doing so, the stars appear fixed, yet they too are moving, each following its own path through the galaxy. Change is everywhere, but it often unfolds so slowly that it feels like stillness. That stillness can be a gentle place to rest the mind. You do not need to hold all of geological time in your thoughts. It is enough to remember that the world is vast, that it has endured, and that you are here, in this moment, part of a story that began long before and will continue long after. The landscapes of Colombia are gone, the oceans that surrounded it have vanished, and the mountains that rose during its formation have been worn down and buried. Yet the processes that shaped that world are still at work, shaping the one we know now. And as the Earth continues its quiet turning, as night deepens and the world grows calmer, the long history of the planet becomes not something distant and abstract, but something steady and reassuring, a reminder that time is vast, the world is patient, and there is a certain peace in knowing that the rhythms of nature move gently onward, carrying us with them into the quiet of the present moment.